Morning. You awake? I know it's always funny when I get the Saturday lecture because people kind of, yeah. So fortunately, the topic will wake you up and make you excited and energetic. I really love coming back to Lisbon to teach this class on sequence models, and I'm really, really lucky because even though we work in a very high-paced, fast-changing research area, natural language processing, machine learning, artificial intelligence, things are moving very, very fast. The great thing about this content, about today's lecture, is that I could have taught you pretty much exactly the same thing 30 years ago. Well, I couldn't, I was very small, but someone could have, and it would have been very similar. So I think I'm really lucky that I get this sort of foundational stuff. So today you're going to learn some of the fundamentals. We're going to focus on Markov models and hidden Markov models. And if someone asks you, did you learn anything really new and exciting today? Maybe the one sort of point to remember is today you're going to learn why we call the hidden units in a neural network hidden, and some other more important things probably. So just to give a quick outline, I'm going to start off by talking about Markov models as a way to model sequential data, like text or speech. And then after we talk about Markov models, we're going to quickly move to hidden Markov models, which are the more exciting and broadly useful tool, generalization. And in order to really work with hidden Markov models and successfully use them in your work, you have to understand the algorithms that we use for doing inference and learning with them. So we'll talk about inference, starting with a classic algorithm called the Viterbi algorithm. It was invented in the 1960s, before any of us were born. And then then we'll take a coffee break, and it'll all soak in, and you'll come back reinvigorated, and we'll talk about other inference algorithms for HMMs and learning. Okay, and because I teach in the United States, I have this sort of expectation that I will not stand here and talk until the coffee break and then come back and talk for another hour and a half. If I do that, I will lose my voice. So you should raise your hand if you have a question. Good? Okay. One thing I always do at the beginning of this lecture, it's embarrassing, but I do it anyway. I wrote a book a while back. I wrote it for you. And it covers a lot of the topics that we talk about today, and also a lot of the topics that you'll hear about in the next few lectures from Xavier and from Slav. It's pre-deep learning, so I'm sorry, there's no neural networks in this book. But again, a lot of the foundational ideas from natural language processing and using machine learning in NLP are covered, and I think it's often helpful to have something to kind of refer to that's text that you can take at your own pace in addition to hearing a lecture. So if you want something to read, I think this is maybe the best thing going in terms of a set of notes that tie together this lecture and what you'll see a little later. Also, if you are a student at a university, it's quite likely you can download this for free through your library. This series has a nice deal with a lot of universities. Okay, so let's start Markov models. When we take a data-driven view of natural language, and we think about the data that we have to understand natural language, we think of text. And one sort of very simple view of text that's not very controversial is to say that when I have a piece of text, it's a long or short sequence of symbols. And we can think at different levels. We can think of it as a sequence of bytes or letters or characters, or if you want to be sort of linguistically oriented, morphemes or words. Right? Text is a sequence of words. So let's formalize that a little bit. Let's let the set of symbols in our language be sigma. This is sort of a classic notation from the theory of automata and formal languages. And then once we have sigma, when we start talking about the set of possible sequences of sigma, the set of all the possible sequences that could happen, we call that sigma star. Familiar notation to some people, maybe? And that's infinitely large, right? There are infinitely many sequences. Even if we have a finite set of symbols, we can build arbitrarily many different sequences of those. So what I want to start off is getting you thinking about is the idea of a probability distribution over the infinite set sigma star. Very large set. OK, so now I'm going to give you a quiz. So right now, this idea I've just proposed of having a probability distribution over sigma star, the infinite set of all sequences of symbols, Am I being generative or being discriminative? Who says generative? Who says discriminative? OK, almost unanimous and almost all correct. Good. So this is sort of referring back. Hopefully you learned about this yesterday from Shai. Did he spend more time on one or the other? More on discriminative models. OK. OK. So today we're going to be almost all generative. Yeah, I think 100% generative. They're both useful. There's not a value judgment here, but they have different strengths and weaknesses and different uses. And I think it's helpful to review quickly the difference. So generative models, they tell us a story. We look at our data and we say, what were the things that happened in our abstract universe that gave rise to this data? Kind of like the Christmas story, right? We don't necessarily believe the story to be the true account of why the data are the way they are. It's an abstraction. Often it makes simplifying assumptions, but it's still quite useful. Christmas is useful, right? The other version, the other kind of machine learning that we use fairly frequently in NLP, and I think we saw some of this yesterday in Yejin's talk, are discriminative models, where we say that there's a task to be done, like we need to sort out a set of examples. And so the idea is we focus on that task and we train a model that does really well at solving a particular task, like the sorting hat in Harry Potter. Yes?
So I still don't quite understand how I get from just saying I want probability distribution over my alphabet to it's going to be a generative model. I mean, all there also like linear language models and stuff like that.
So I would say a log linear language model is a generative model. If there's there's not a single formal definition everyone agrees on for these terms, but in my view, if the model defines a data generating process over the data you observe, inputs, outputs, doesn't matter, it's generative. Okay. Sometimes it gets a little bit gray because there might be some aspects of the model that are slightly discriminative, or we may be seeing some discriminative procedures being used, or people may be not normalizing their probability distributions, and then you can ask, is it really a probability distribution? There is a gray area, but if there's a probability distribution and you're using maximum likelihood estimation, it feels pretty generative to me. OK, so let's come back to sigma star. Here's a really, really trivial distribution that you could define. It's somewhat uncomfortable to think about an infinite set and spreading probability mass over this infinite set. One way to do it is to zero things out. So basically, define a distribution that says if the sequence has length less than or equal to some upper bound b, then it gets uniform probability because that set is finite, and then everything else gets 0. Not very satisfying, but it's a probability distribution. We just sort of say long sequences can't happen under this model. That's one way to do it. Another way to do it is to take a collection of sequences that we observe in data and just do literal maximum likelihood estimation where we assign probabilities to sequences. So we say 1 over n for each sequence in my data, if I have n sequences, and 0 to everything else. Okay? That feels sort of wrong. Why does this feel wrong? Why don't we just go home? So the issue here is that this isn't going to generalize very nicely, right? We really want to have a model that can assign probability to sequences we haven't seen yet. And we want our model to sort of cope with surprise well. So if our model gives 0 to any sequence it didn't see in the training data, it's just not going to generalize nicely, right? It's just going to, you show it a new sequence that was, and almost any sequence in the universe is not in our training data, even if we have a lot of data because there are infinitely many sequences. Then our model's going to come back and say 0. I don't know. I've never seen this. This can't happen. And that's not very useful. So what we really want is some kind of probabilistic model family that construct a model from data that will generalize. And then we need algorithms to work with that model. So that's our starting point today. Here is a very, very simple model that is hard to argue with in terms of the assumptions it makes about the data. So I'm going to start introducing notation. We're always going, when we think about sequence models, it's quite useful to imagine that anytime you observe a sequence, you observe a special start symbol right before it and the special stop symbol right at the end of it. Okay? And it's not really controversial. It's just kind of helpful notation. So what we want to talk about is the probability of seeing start and then a sequence of words W1 through Wn and then stop. And so one way to define this model is just using the chain rule. We're going to imagine that each word was generated in turn from the beginning up until the end, conditioned on the words that came before it. Okay? Nothing controversial here. We've made no additional assumptions about the data. We just have distributions over word given history, all the way back to the beginning of the sequence. Okay, and I'm going to use gamma to mean a parameter for this conditional probability of word I given the previous words, I1 through I minus 1. Okay, so sometimes I think people understand this stuff better and remember it better if they can imagine a physical process for generating the data. So we're going to get very literal. Small English lesson. You know this word die? The noun? Do you know the word dice? Like you go to Vegas and you roll dice, right? The singular of dice is die. This is one of the most strange words in English. Okay? Right, this is probably all the linguistics you'll get today. So 1 die, 2 dice. In this model, we actually have a lot of dice. For every possible history that could ever have occurred, we have a die. And what happens in the model is we start by writing down the start symbol, and then we go to our huge pile of dice, and we pick up the one that says history equals start. We pick up that die, and then we roll it, and we see what word comes up. And say the word that comes up is the word I. It comes up on top. So these dice, they have more than 6 sides. They have like thousands of sides, tens of thousands of sides. So like, big polyhedron with lots of faces. It almost looks round if you go away at a big distance. But it lands on one side. You write down the word I. Then you have to go find the die that says start I. So you go find that die and you roll it, and it comes back with want. And now you have to go find the die that says start I want. You go pick it up, you roll it, and it comes back and says A, and so on. So every time we generate a new word, we have to go get a die with a longer history. So now we've got to the point where we have a die that says start I want, A flight. Pick up that die, roll it. It'll give us a probability over words. It says 2. We get Lisbon the next time. Keeps going. When you pick up the die that says start I want a flight to Lisbon, it's likely to come back with a full stop. And then a real stop after that, maybe. So how many dice do we have?
As many as sequences?
More than the number of sequences. It's more than the number of sequences in the data. We actually need one for every sequence in the universe, because every prefix that doesn't end in stop is going to have a die so that we can figure out what comes next. That's a lot. We don't have enough data to estimate all those probabilities. Okay, so this is not a model anyone would ever build, at least not the way I've described it. Not with that many dice. That's too many. But the good news is that it's very rich. You can capture any distribution over sequences this way. It's sort of infinitely flexible, and that's the problem, right? From a machine learning point of view, it's a very powerful model, but it requires essentially infinite data to estimate. It has too many parameters, an infinite number of parameters, and it's still not clear what's going to happen when I see a sentence that was not in my training set. So suppose I look at some data and I train up a model, and then I get a test sentence that I haven't looked at before, and I ask what's the probability. Well, if it has a prefix that I never saw in the training data, it's not actually clear what my estimate should be of the probabilities of the words that come next. Okay, so this is sort of unclear how to build this kind of model. So so let's set this aside and say that was an option. This is probably not a practical one, but it's good to think about it. I'm going to present a different model. It's called a bag of words. Have you heard this phrase? In the department I used to work in at Carnegie Mellon, there's actually a physical. I should put a picture of it. There's a sculpture, like an installation art piece. It's a big cellophane bag with a bunch of words in it. And some of the words have fallen out on the floor. It's really funny. It's called the bag of words. It's very memorable. OK, so here's the idea. In the bag of words model, same thing. We're writing down the probability of start, word 1, all the way up through word n, stop. And we write it as a product of a probability of each word in turn, not conditioned on anything. Okay, so we just have a distribution over words, and each time we generate a word, we roll the same die. The whole model is one die. Each word, you pick up the die, you roll it, you get the next word. Okay, so start, I want a flight to Lisbon. It's very boring. Each time we just roll this die, and it forgets. It doesn't remember anything about what was already generated. And then we generate a stop. Okay, every word, the way we say this mathematically, is that every word is conditionally independent of every other word. And this is a model that some people really find beautiful, and some people are really troubled by it. Anyone really troubled by this? This is not the way language works, right? This is not, nobody believes this is a true story. It makes very strong assumptions about words. Right? If you understand how, if you've spoken language your entire life, if you've learned a foreign language, if English isn't your first language, you know that every word is not, there are all kinds of interdependencies among the words that we say. So these independence assumptions are clearly wrong, and that means we can't fit our model very well. Right? The data are more complicated than this model likes to assume. But the good news about this model, on the other hand, the pro, is that there are not that many parameters. You just have to have one die. It has one probability for every word plus the stop symbol. So it's, the number of degrees of freedom is just the size of your vocabulary. So the amount of data you need to estimate this model is nowhere near what we would have needed for the infinite history, never forget anything model. Another nice thing about this model is that if I give you a sentence that was not seen in the training data and ask you to compute its probability, if the sentence is n words long, what do? You look up each word in turn in the table, and you multiply those probabilities together. And if all the words were seen in the training data, or you gave them all probability anyway, you're fine. You're not going to get a 0. As long as every word has non-zero probability, you're going to get a number that means something. So the model can predict. It can generalize. And that's a good thing. Okay, so I have done what philosophers call I have created a straw man, 2 straw men actually. So I've given you one model that's obscene because it has too many parameters and it can fit any data, and then I've given you another model that's incredibly crude and simple. And it can generalize well, but it doesn't really fit the data that well. Now I'm going to give you a happy medium. Okay, I'm going to give you a family called Markov models. We're going to start with something called the first order Markov model. The first order Markov model says that each word is generated not conditioned on all of the history, just the most recent word. First order, yes. Oh, you're, OK, sorry. Misunderstood. So you're just going to condition on the most recent word in the history each time. And so your model looks like this. You've got a product over all the words of the word given, word at the position I, given the word at position I minus 1, the previous word. If we want to look at what this looks like in our pretend physical universe, where wherever language is generated, this is somewhere in your head, there are these little people rolling dice. And there's one die for every history. The histories that we consider in this model are the previous words. So we have one die for every word in the vocabulary. And that corresponds to that word being the history. And then when we roll that die, we're picking the word that follows. So we pick up the start die, we roll it, and we get I. We pick up the I die, we roll it, and we get want. We pick up the want die, and we roll it, and we get A flight, and so on. So this model is sometimes called a bigram model because each of the parameters is associated with a bigram, 2 words that are occurring in sequence. The bag of words model we saw a minute ago is sometimes called a unigram model. That's its other name. 1 word, unigram. And then, of course, we have the stop symbol. So this model is making a conditional independence assumption. It's assuming that each word is independent of everything that came before, conditioned on the one word that is most recent. And this is called, in mathematical terms, we call that a Markov assumption. And it's quite useful. The reason it is useful is that it reduces the number of parameters from the infinite history model down to how many? How many probabilities are there in this model? It's the square of the size of vocabulary. There's one die for every history, and each of those dice has size of the vocabulary plus one sides for the stop. Okay. So sometimes people think of the parameters as living in a big matrix where, I don't know, rows are the preceding word and columns are the word that comes next. And each column, each row would add up to 1 in that case. You could also take the transpose. Yes?
That's a bit too much because you don't really have every word associated with each word. It's less than
Well, maybe it's too much, maybe it's not. So that's a great question. Empirically, it's actually not too much. Empirically, we actually, now that you've seen the unigram and the bigram, you can imagine going to 3. And empirically, when I was a grad student, everyone knew you could estimate trigram models with reasonable amounts of data. That was a long time ago. Nowadays, in real systems like machine translation, they use 5-gram models without batting an eyelid because there's data. Now, you're not going to observe every 5-gram in the universe, but there are some tricks that let you share statistical strength across the 5 grams and smooth the model out. Okay, so that's a big topic. We're not going to get into it today. In fact, these models actually do generalize pretty well until the history. There's always a point where the history is just too big and it doesn't work anymore. So we're getting ahead of ourselves. What's going to happen when I look at a sentence that's not seen in training data? You're kind of getting to this point with the question. If every bigram in my sentence was seen in the training data, then I'm good. I'll have estimated a probability for it. If the sentence has a new word or a new bigram, then I might run into trouble if I have a 0. So the model has some risk of not being able to recognize new sentences, not being able to give a non-zero probability to a new sentence, which is why often, typically, when we build these kinds of models, we do something to smooth out the probabilities. But we only have to smooth over those vocabulary size squared entries in our matrix. That's all. So generalizing slightly, at one extreme we had the bag of words. The next thing over that we had, and at the other extreme, we had the entire history model that remembers an infinite history, too many parameters. There's this sort of middle ground, which we'll call, in general, mth order Markov models, where you remember m-1 words of history. As you increase m, you get richer expressive power, but you also have more parameters. So I introduced the unigram model over here at 0 and the bigram model here at m equals 1. And you can imagine conditioning on increasingly more history. Just for fun, I'm going to show you examples of data generated by different order Markov models, just by randomly sampling. So I estimated the model on about 3 million words of text from American political blogs. So I like politics. And then I literally simulated rolling the die and looked at the words that got looked at the sequences of words that got generated. We don't really use language models this way usually, but it can help you kind of see what the model knows and doesn't know. So this is sampling from a unigram model. This trying our pudding and funny and among it herring it Obama, but certainly not English, right? Not English. Bigram model. The lack of the Senator McCain hadn't kept this story backwards while showering praise of the kind of GOP weakness. There are a couple of things in there that are like Senator McCain, right? That you couldn't get that unless you had seen that pair of words reasonably frequently, right? That's a good pair, right? So locally, it starts to get better. Trigram model starts to get better. As I can pin them all, none of them want to bet that any of the might be conservatism unleashed into the privacy rulebook, and when told about what Paul, almost, right? If you were half asleep, hadn't had your coffee yet. Here's the 5-gram model. He realizes fully how shallow and insincere conservative behavior has been. He realizes that there is little way to change the situation. OK, don't be too impressed. It's memorizing. That's the creepy thing about these models with longer history. They just kind of start memorizing the data. Right? If I had an infinite history model and I sampled from it, like here's an 100-gram model, it's just spitting back sentences from the data.
And it would be the work of many hands to catalog all the ridiculous pronouncements made by this man since his long train of predictions about the Middle East has been gaudily, disastrously, stupefyingly misinformed. It's like, this model is not that smart. It's just memorizing what it's on the training set. Okay. I think it's actually useful. NLP is a really nice vehicle for understanding basic concepts in machine learning because we all have intuitions about language. We can all recognize good language and bad language in languages that we know. And so understanding this idea of overfitting and simply memorizing your training data, that's something that comes up across machine learning, but it really drives the point home to see it with text. Text is very familiar to us. OK, so N-gram models in general, the N-gram model is the sort of general name for applying Markov models to text. They have some pros and cons. On the plus side, I say that they are the easiest to understand linguistic formalism. And when I say that, my friends who are linguists get angry because they say it's not a linguistic formalism. And I say it absolutely is. It's a linguistic formalism that's extremely simple, that makes very naive assumptions. It doesn't describe everything we see in language, but it is formal, and it's describing language. Fully generative describes a probability model over the data. Let's talk about algorithms in a minute. I want to talk about the cons, and then we'll come back and talk about the algorithms that you need if you're going to adopt an N-gram model view of the world. The downsides of N-gram models, well, first, like my linguist friends will say, it's not an accurate view. It's not an accurate formalism. It doesn't actually capture all the interesting things that happen in the phenomenon of human language. Data sparseness, as n gets bigger, as you have longer and longer histories, you don't have enough data. You will eventually run out of data to accurately estimate probabilities. So there is this sort of solution, half solution, called smoothing, which lets us use N-gram models even though they're not perfect and even though we don't have enough data. But smoothing is complicated. It's a black art. I could give you a 3-hour lecture on smoothing. And there are complex software packages that are typically used to accomplish it. The basics are actually not that hard to understand, but why some models for smoothing work well and others don't is still not, I would say, not especially well understood. Another issue that comes up with N-gram models is when you see a word you have not seen before, your model doesn't always have a good solution for that. So there are some tricks that people use to handle unknown words. But N-gram models, they really don't generalize beyond the words they've seen. OK, so if we're going to adopt this view of language, then there are 3 things I think you need to sort of basically understand how to do. And if you understand them for N-gram models, it will be helpful in understanding them for more complicated models. So the first thing is if I give you a sequence and an N-gram model, calculate the probability of that sequence. This is useful for evaluating your model on new data. Another is if I give you a set of sequences and an N-gram model, choose one from that set. And the last one is how do I estimate the probabilities? Okay, and you probably have intuitions about all 3 of these, and none of them are going to be all that surprising. Okay, so let's talk about the first one. I'm going to give you a sequence. Suppose that it's n words long. And we're going to use an mth order language model. So that means that each probability is conditioning on m minus 1 previous words. So the way this will work, it's very simple. For each of the words in turn, going from 1 to n, I'm going to look up the history. And then I'm going to look up the probability of the next word given the history. Okay, so now I've got n of these things plus 1 for the stop symbol at the end. What do I do with them? I multiply them because of the chain rule. Right? All I'm doing is I'm implementing the chain rule. I'm saying that the probability of the joint probability of the whole sequence is the product of the probabilities of each of the individual events conditioned on their histories. Make sure you include the stop symbol and multiply. Pretty easy, fast, linear time in the length of the sequence. If you're good at implementing data structures, you can make this very fast by storing these tables in an efficient way. If I give you a set of sentences and ask you, which one should I pick? So one case this comes up is if you're doing speech recognition
or machine translation, and you have a way to propose a set of candidates, and then you want to use your n-gram model to choose one that is reasonably likely, one that is expected to be fluent under our n-gram model. First, calculate the probability of each of the guys in the set. And then what? Take the most probable. It sounds reasonable to me. Right? Very useful. Sometimes what we actually do is we combine our n-gram model with another model. And I'll come back to that idea in a couple of minutes. But if I simply gave you no other information and said, here's a set of sentences, which one do you think is likely to be good? Your n-gram model gives you a way to do that. That's one of the very few things it can do. So if you remember yesterday's talk where Yejin talked about automatically generating captions for images, you could imagine using an n-gram model to choose among a set of candidate captions. And in fact, she did use an n-gram model. I think she may have mentioned, you may remember vaguely, there was a lot of math, but one of the things she mentioned was a language model. That's what this is. OK. Another relatively simple thing that people usually have a good intuition about is, how do I estimate the probabilities? How do I train this model given some data? Okay, the simplest thing to do is called maximum likelihood estimation. That's a very fancy term for counting. Count up the number of times you saw a unigram or a bigram or a trigram and divide it by the number of times you saw the history. This is called relative frequency estimation. It's another fancy name for counting. And you can prove that if you do relative frequency estimation for this kind of model, you are getting the maximum likelihood estimate. You're getting the estimate, the probability estimates that give you the highest probability of your training data. In fact, when we train language models, we don't usually use this directly. We usually seek a somewhat lower likelihood estimate that will generalize better. And that's where smoothing comes in. OK. Language modeling, still a somewhat active area of research. A couple of things that have happened in the past 5 to 10 years. More data. And so people have developed tools for handling very, very, very large amounts of data and still estimating n-gram models that are very fast. One interesting thing is, it's always kind of been known, but it's surprising how long it's held up. The more data you have, the better your language model gets, even if it's a simple n-gram model. As we get more data, what we've seen over the years is longer n. Longer histories, longer n. So a lot of focus in the past few years has focused on, a lot of the research has focused on making these things very efficient, whether that's using MapReduce architectures to look at a lot of data at the same time in building your model, or compressing a model down to something very small with approximate probabilities so that you can get very, very fast lookup when you're running a real system that uses a language model. So that brings me around to, what are these things really used for? Nobody, to my knowledge, nobody in any real system takes a language model and just samples from it the way I did a little while ago. That's not really how they're used. They're really used as a component in some kind of analysis or generation task. So one version of this is, I get a sequence in, and I'm going to predict some other thing. And a language model can be a component there. Or I get something else, like images in last night's lecture, and I want to generate a sequence. And a language model can help me score sequences. And they're actually used in both cases. So I'll give some examples. The general paradigm for putting these together is often described as the noisy channel, which is a very classic tool from information theory. It captures a lot of the modeling that we do in NLP with text. In a noisy channel, you have a random variable y that is sampled first according to some model called the source model. And I like to think of y as sort of, it's the truth. It's some beautiful thing. The source model generates something beautiful. And it's a probabilistic generative model that gives us some beautiful thing called y. And then what happens is this true y goes into something called the channel. And I think of the channel as a blender that takes that perfect, beautiful thing and scrambles it up somehow. It chops it up or somehow does something to it. And what comes out of the channel model is x. X is a different observation. X is actually what we see. We don't see y in our data. We only get to see x.
And so, the goal when we see x is somehow to recover y. And we usually use the term decoding to recover this true y, the thing we want, given the thing we observe. Okay, I'm being very abstract, right? The thing we observe, the thing we want. But this captures a huge number of problems in text processing, and not just text. The key trick to decoding when you have this noisy channel set up is to say what you want is to pick the y that maximizes the probability of y given x. It's the most likely y given x and our modeling assumptions, the source and the channel. If we've written the model this way, then we can use Bayes' rule to turn it around and say what we really want is to maximize the product of the source model, p of y, and the channel model, p of x given y. In other words, give me a y that makes the observed x likely, given that y, and is likely on its own. I'm trading off two things, the source and the channel. OK, so the sequence model can actually be either of these. In many applications, it is the source model. So in speech recognition, p of y is usually an n-gram model over sequences of words. In speech recognition, your output is words. You want words to come out, and you're imagining that these acoustic signals that you've observed are actually a garbled, blended up version of the true, beautiful text words that went in the beginning. And so your goal in decoding in speech is to recover the words. Similarly, in machine translation, you observe some Chinese, and you imagine that the Chinese is a garbled up version of the true language English or Portuguese or whatever. Okay? We don't believe this is true. It's just a useful abstraction, and we can end up using a lot of the same mathematical machinery to try to decode and recover. Optical character recognition has been treated the same way. Spelling correction, lots and lots of problems. Put a language model up there for the source, and then describe some process by which words get garbled up into something else. Sequence models are also used as channels. So one example is text categorization. We imagine that first a true label, the category of the text, was generated, and then somehow it went through a channel and these words came out. And now our goal is to recover the true label of the text. In that case, what we have is a conditional language model for each label, saying what words are likely under that language, under that category. Similar things are used for language identification. Information retrieval can be cast this way. Lots of other problems. OK, so n-grams are very, very powerful, useful way to do language modeling, very, very fast. They can fit the data really well, especially if you can smooth and you have a lot of data. For some problems, n-gram models are not the best thing that you can use. And so depending on your task, depending on your assumptions about the data, what you know about the domain, what you know about language in general, you can often do better. And so what I'm going to do for the rest of today is focus on a different kind of model that's using some understanding of the way language works and some more powerful generalizations to give us something that's a little bit more interesting. Okay, but I think you shouldn't really try to understand the next thing until you've got markup models. Who's seen them before, by the way? Who's familiar with markup models? OK, let's move on. So here's a nice generalization that's a little bit more interesting, called class-based sequence models. This is old. This is 25 years old. The idea is that you're going to define the joint distribution of the sequence, start followed by a sequence of words followed by stop, using two parts. The way to think about it is that every word belongs to some class. So I'm going to use the function CL to define the mapping of words to classes. And there's a smaller number of classes than there are words. And we'll assume that we know the classes of the words, and they're deterministic. Every word belongs to only one class. And maybe we have some algorithm for discovering the classes. Maybe they're handed to us by someone else, but they're known. And so our model tells us that the probability of the next word is actually it involves two steps. First, I'm going to generate the next class given the previous class, and then I'm going to pick the word given the class. So what I have is essentially a bigram model over classes, and then a model that turns classes back into words. So the way it works, first I start, then I go to my next class given previous class set of dice.
I have number of classes dice. Each one gives me a distribution over the next class. I pick up the right one, the one for start. I roll it. I get C53. And then I go to my other set of dice, the red ones. There's one for every class. It's got words printed on it. I roll the one for C53, and I get a word, I. Now I go back to my black dice, and I pick up the C53 die for the history, and I roll it, and I get C23. And so I alternate back and forth, rolling the black die to get the next class, the red die to get the next word, and so on. Make sense? That's the formula. The independence assumptions here are a little bit more complicated. What I'm assuming is that each word is not independent of the previous word, but it is conditionally independent of the previous word given their classes. Okay, so it's really through the classes that there's sequential information passed along. The words are conditionally independent given the classes. They're weakly dependent on each other through the classes. How many parameters does it have? I'm hearing it muttered that there's number of classes squared for the bigram model over classes. And then there's got to be one probability for each word given its class. So it's size of vocabulary plus number of classes squared. So this is actually a lot better than a bigram model. Far fewer parameters. If I have really good classes, this could be really nice because I have a lot less. Less parameters means maybe I can estimate from less data. Generalization ability? Well, as long as I know all the words and their classes, I should be able to do just fine. I should be able to do pretty much anything as long as the distribution of next class given previous class isn't sparse, as long as I don't have zeros there, and I've seen all the words. Again, the unknown word problem is still going to haunt us. OK. So that's sort of a nice step towards what we're going to do next. Yes, question?
Would the classes be part of speech tags?
They could be anything. So they could come from linguistic knowledge. They could be handcrafted. They could come from some kind of automatic clustering algorithm. In the original paper by Brown, they came from a clustering algorithm. OK, yes, question? Say that again?
What's the usual practice for clustering the words is based on the context of the...
Could be. Yeah, that's a common thing people use for word clustering. But it could be anything. Yeah, notice I'm not making commitments about the specific details of where we get the classes. I'm just supposing that there are. Lots of ways to do it. Yeah?
But does it work better than just mention one?
So in the original paper, they showed that it did work well under assumptions of data that they had back in 1990 and ways of measuring success that they had back in 1990. Nowadays, I don't think anyone uses class-based language modeling out of the box quite the way I described it. I teach it mostly as a stepping stone to get to the next model. Yeah.
Actually, we are using it in spoken dialogue systems because we have the classes like bus stations or cities.
Awesome. So I'm wrong. It's still useful. But it's domain knowledge that's giving you the classes. Yep. OK. Moving on to HMMs. Hidden Markov models. Who's seen HMMs taught before? OK, excellent. And who feels ready to stand up here and teach them for me? So the thing about HMMs is if you feel like you've seen them before and they're still confusing, that's because they are hard. For whatever reason, I don't know why, they're hard to get until you've seen them 2 or 3 times by different people with slightly different notation and with slightly different style of presentation. So hopefully this is the time you will completely master it and you'll feel ready to teach this lecture for me next year. HMMs I really think they're one of the most powerful. Once you understand them, a lot of other things become far more clear. They're just a nice point in the pedagogical space. OK, so HMMs are like the language models we just saw. They're models over sequences of symbols. But they make this funny, they have this sort of funny extra assumption that there's hidden information, missing information associated with each symbol. We call that its state. And so what we assume is that there's a finite set of states
call it lambda, big lambda. And when we define the probability distribution, we're actually going to define the joint distribution over the sequence of symbols, W1 through Wn, like before, and also the sequence of hidden states, S1 through Sn. So there's one state per word, and we have to define a joint distribution over both. And the form of that distribution looks very similar to the class-based model that we just saw. Each time we generate a word, we first have to generate its state given the previous state, and then we generate the word given the state. Two things get multiplied together. The difference from the model we saw before is that the states are not known. We can't simply look at a word and then go to a table and say, oh, this goes in the bus station class, or this goes in the city class, or this goes in class number 73. We actually don't know. There's ambiguity. Okay, so you have to remember HMMs are a joint model over the observable symbols and their hidden, latent, unknown, missing state information. So here's the generative story. It looks very similar to what we had before. First, we start by going to the what we call the transition distribution for the history, for the start symbol, and we randomly draw from it. We get C53. Then we go to the red die, what we call the emission distribution for state number C53, and we roll that die and we get a word. Okay, so this is just like the class-based language model, except instead of each word being associated with only one of these dice, every word could potentially be on every one of the dice. So when you see a word, it could be potentially with any of the states. Once we have our word I, we go back, we pick the transition die for C53, we roll it, we get C23, and so on. We keep alternating back and forth, just like before. And there's actually two ways you can tell this story. One of them is the way I just did it. First transition to a class, black die, then emit a symbol, red die. Then transition to the next class, black die, then emit a symbol, red die, back and forth. Another way to do it is to first do all the transitions and generate a sequence of states, and then go back across those states one at a time and replace each one with a word stochastically by rolling its red die. Some people like the second story better. They are the same. It's up to you. When you teach it, you choose. Okay, just like with Markov models, we could go to mth arbitrarily large order. We can do the same thing here, and we can condition each state on a longer history of past states. So here I'm conditioning on m-1 previous states. Okay, quick check on our model. How many parameters do we have? Well, for the emission distributions, we now have one die for every state, and it could range over the whole vocabulary. So we have size of lambda times size of sigma, number of symbols. For the transition distribution, if it were a bigram HMM or a first order HMM, we would have number of states histories times number of states as events. So you have lambda, size of lambda squared. But as you increase it, just like with an n-gram model over words, you're going to increase that exponent. So if you had a second order model, you would actually have to have lambda cubed transition probabilities. Typically, when we build HMMs, lambda is much smaller than sigma. And so having higher order models, trigram or 4-gram HMMs, is not completely out of the question. And we may not even need as much data because we have fewer parameters. Okay, as you add longer histories, what you're doing is you're allowing your model to remember more from the past. Right? That's sort of the intuition. You're remembering the past, but you're abstracting away from the particular words that you saw. You're only remembering their states. Okay, because the math starts to look hairy on the slide, and there are a number of formulas I want to show you as we keep going, I'm going to stick with first order HMMs today. Okay, but I want you to keep in the back of your mind that everything I'm showing you generalizes to higher order HMMs with longer histories. And I want to actually point to a few different examples of how HMMs have been used in NLP. I'm going to focus on NLP. It's what I work on, but HMMs have also been very, very useful in computational biology. And they're I think, the most important thing you have to learn if you're going to do speech recognition. And they come up in lots of other fields as well. They're usually somewhere in, if you have a machine learning textbook, they're somewhere in that book. If you're going to model sequences, you kind of have to know about HMMs. Let's focus on the language examples because I find many people find that they are intuitive. The first one, the classic one, is part-of-speech tagging. So part-of-speech tagging says that what we want to do is label each of the words in a sentence with an abstract category corresponding to a sort of syntactic class. And so the codes that you see in blue are, they're from a data set called the Penn Tree Bank, which is, I don't know, 20 some odd years old. And these categories were sort of designed by a collection of linguists at the University of Pennsylvania. And the codes are hard to remember unless you've seen them a million times, but RB means adverb. If it starts with a V, it's some kind of a verb. DT is determiner. JJ is adjective. Some of these words are probably familiar to you, even if you haven't taken linguistics. Some of them are sort of not really linguistic. They're just things we see in text, like punctuation. But the idea is that each of these words can be labeled with a part of speech. And some words are ambiguous, and it depends. The context affects which part of speech they should get. So the word broke here is an adjective, but broke is also a verb. In this case, we can tell that it's an adjective because it's I don't know, it's the right argument of this verb to be. It's a copular construction. No, copular construction. OK, so we can use an HMM to solve this problem by letting the states correspond to the parts of speech and inferring the set of parts of speech given the words that we observe. We'll get back to the algorithm for doing that. Another problem HMMs are used for is in information extraction when we want to find spans of words that refer to some kind of real-world entity. So in this case, I've colored in red and purple and green different entities that are mentioned in the sentence. The way that we can label these is we can encode in the labels whether a word is outside any named entity, for which we use O, whether it's the beginning of a named entity, for which we use B, and then the type of the named entity, person or place or space shuttle or whatever, city, whatever categories of named entities you're looking for. And then we use I for inside. So this allows us to see that Kennedy Space Center all goes together. It's not three different named entities. For that, we would call it B place, B something, B something. So these BIO labels are a nice way of encoding sort of segmentation within the states. So if each label is a state, we can build an HMM that learns to figure out where the named entities are. Another one that's a little bit surprising is that you can use HMMs to align words in parallel text. So if we have this sentence in English and its translation in German, and what we want to do is figure out which words in German correspond to each of the English words. There are a lot of nulls because there are a lot of extra words in English that that you don't need in German, or you don't or get swallowed up in some other information like the morphology. The idea here is kind of clever. You let the German words be the states, and you imagine that each of the English words is generated by sampling from a state corresponding to the German word. So we have a null word for all the things that are not on the German side. We transition back to the null word. We generate another word. We transition back to null. We generate another word. Now we transition to this German word, and we generate the English word, and so on. And we walk around the German sentence. Each time we get to a new word, we generate an English word. This is a very successful model for aligning words across languages. OK, so that's the HMM. Those are some of the things it's used for. As we go forward, it'll help if you have the notation in your head. So I'm going to use eta for the emission distribution of a word given a state, and gamma for the transition distribution of a word given the previous word. A state given the previous state. All right. We have a half an hour before the break?
Yeah.
All right. Excellent. Questions? Should we do the algorithm? Viterbi? So when we use HMMs,
because we have these hidden states that we don't observe in the data, everything we might want to do with the model becomes a little bit more complicated than in a model that is simpler and makes stronger assumptions about where the data came from, like a Markov model. So here we are. We have half an hour left before the coffee break, and then another hour and a half after that. And we're going to use all of that time to cover a set of algorithms that you might use if you're using HMMs. Fortunately, these algorithms are all related to each other. So once you get the first one, they all sort of start coming together. So by the end of the lecture, it will all feel very unified, I hope. But the first one is, if you have an HMM and you observe a sequence, can you calculate the most probable state sequence that goes with the words? Okay, so in other words, if our HMM is for part of speech tagging, find the parts of speech for the sentence. And then we get to some more complicated problems, like here's a word sequence. Give me the total probability of the word sequence. Now, if you think about that, our model doesn't tell us the probabilities of word sequences. It tells us the joint probability of words and states. So in order to get the probability of just the words, I have to sum up over all the possible state sequences that could go with those words, of which there are many, exponentially many. The third thing we might want to do is ask for a particular word in our sequence, what is the probability distribution over states for that word conditioned on the whole sequence? Okay, each of these is sometimes called an inference problem. The last one we'll come back to is called finding the minimum risk sequence. It's a different way of picking a sequence. And then the last thing we'll talk about is how do you get the parameters given data? And there are two versions of that. There's the supervised version, where I give you states with sequences. That's pretty easy. And then there's the unsupervised version, where I just give you or just sequences. I just give you the words, and I ask you to estimate the parameters of the HMM from the words alone. That's an unsupervised problem. It's harder, but we'll also talk about that. OK, so problem one, find the most likely state sequence. I'm going to give you an HMM, which is essentially its parameters, the gammas, which are the transition parameters, and the etas, the emission parameters. And I'm going to give you a symbol sequence. And what I want you to calculate for me, in precise terms, is the sequence of states that is most probable given the words and the parameters. Okay, if I want to talk like a statistician and I want to use fancy words, I would call this the maximum a posteriori sequence. I would call it sometimes called map inference, maximum a posteriori, most probable in the posterior. If I am a computer scientist, then the way I'm going to look at this problem is that I'm solving a discrete combinatorial optimization problem. Okay. Yesterday, you got a little bit of a preview of the set of techniques that we end up using to solve this kind of a problem. And the good news is you don't have to use integer linear programming. You can solve this problem in polynomial time and space using dynamic programming. You're not smiling. You should be happy. This is good news. We're going to do something amazing. We are going to search over an exponentially large space of possible sequences, and we're going to do it fast in polynomial time. That's cool. You should never lose the wonder that you feel the first time you discover dynamic programming. OK, so here's my example. At the top is my sequence. I suspect the present forecast is pessimistic. For each of the words, I have listed a set of parts of speech which could go with that word, or which I have observed with that word in my training data. Don't worry too much about what they mean. Just notice that some words are ambiguous. The word pessimistic is always an adjective. JJ is adjective. But other words like suspect can be an adjective or a noun or a verb. Some of these words are 5 ways ambiguous. If I count up the number of possible tags for each word, and then I multiply those together, I find that this little sentence has 4,000 possible state sequences. Yes?
Why do you have these parts of speech for that? It's all in German.
Yeah, I am not sure why the word the is sometimes tagged these other things. I think
there might be some errors in the data.
Well, I was going to ask a question, but part of the answer is probably because the can be part of a proper noun.
So I think when the is part of a proper noun, it's probably usually still tagged as a determiner, but I'm not sure. You know, the annotation conventions for the Penn Tree Bank are actually bigger than the Penn Tree Bank. And there are errors. It's known there are mistakes. But anyway, you had a yeah.
Are the speech tags the states or the sequences?
So right now they're the desired output.
They're the output.
They're the output.
We don't know what the states are.
We don't know what the states are, but when we build our model, we will make assumptions about the state. And the simplest way to do it is to have a one-to-one correspondence between states and part-of-speech tags. That gives you a first-order HMM. If you want to go to a second-order HMM, then you let the states be the previous two tags. Okay, and you can be more complicated. You can add more information or take more information away. But basically, for now, let's just say states equal tags. Labels equal states. Makes it a lot easier. Yes? How are they different from the classes? Right. So they're different from the class-based model because a word like forecast could have been generated here by any number of states. But the class-based model assumed that the word forecast deterministically only went to one state. So it's more linguistically rich because it allows words to be ambiguous. OK, so 4,000 sequences. If this sentence were twice as long, we'd have far more. We are not going to enumerate the sequences. Okay. But let's just humor me for a second and imagine that that's what we're going to do. Just list all the possibilities, all the lambda to the n possible sequences, and then you could score each one using your HMM, and pick the one that's got the highest score, and that would be correct. Okay, but it would not be efficient. Very, very inefficient. But I always think it's good to identify the correct solution that takes too long before you start thinking about the efficient correct solution. Okay, here's another solution that people are sometimes tempted by, and I want to just head it off right away. You could start at the left end of the sequence and go left to right and say, well, given what I've seen up till now, what's the best state I could pick, and then pick that state, and then move on. Sort of greedily choose a state given the word and the previous state. And you could do this. The problem, and you would get an answer. The problem is it's not actually correct. You may not get the globally best sequence of states. Okay, so it's this funny thing that if you make these decisions greedily based on just the most recent past decision, and you latch on to the best thing, and then you just kind of move forward and never revisit the past, you might make a decision that looks good here, and then see a word later on that completely changes the way you should have processed the sequence. There would be no guarantee. This kind of greedy method usually doesn't work very well. Okay, but it would be fast. It would be linear time. You just make a decision at each point. Okay, so now I'm here to tell you that there's a way to get speed and correctness with dynamic programming. Yes?
Has anybody ever investigated how far off this incorrect solution actually is? Because if it's like close enough most of the time, but just go with that.
So probably not this super naive version, but there's a variant of greedy search called beam search, where you keep a few candidates as you go, and it often does quite well. Particularly when you have a lot of states. That becomes the bottleneck for using exact dynamic programming, and there beam search is often quite good. But yeah, sometimes it's a little disappointing. You think, oh, I've got this sort of correct algorithm, and it's really not. You feel really good, and then you go run something cheaper like beam search, and it's as good almost. Yeah, that's life. It's still good to understand the exact algorithm now. Okay, so in that spirit, okay, so here's the kind of issue.
when I think about labeling a given word, so here the word forecast, the label depends, the thing that makes this challenging is that each word's label depends, intuitively it depends on the word, right? I want to know what word I'm trying to label. It also depends on the label to the left, and that's very explicit in the model because the model says you sampled this word's label conditioned on the label of the word present, the word that came before. But it also depends on the label of the word that comes after, because this dependency thing, it's a symmetric relationship. If, yes, the story is that I generate the label for the word is after this label, but it's conditioned on this label. And therefore, the two are statistically dependent. So really, when I'm labeling the word forecast, I have to to make a good decision, I have to know what's happening before me, what's happening after me, and what the word is. All three of these things are weighing in. And they're all, two of those three things are moving, and I'm making decisions about all of these words at the same time. But the key insight is that if I did know the labels on either side of this particular label I'm worried about now, nothing else would matter farther away. Right? There's this first order Markov assumption that says that it's really everything I need to know about the distant past is captured by the most previous state, and everything I need to know about the distant future is captured by the next state. So this gives us kind of a starting point for thinking about how we can efficiently find the optimal sequence. And I'd like to start by thinking about the very last label, because it's even a little bit easier. When I look at the last word in the sequence, imagine that I knew the state of the second to last word. So now I actually have everything I need to make a decision. If I know the state for word n-1, and I know that this is the last word, and so that whatever comes after is stop, the stop state, then I see the word, then I've got everything I need to make a decision. And the decision would be very easy. I simply score each symbol sigma as the product of probability of stop given sigma, probability of the nth word given sigma, and then the probability of sigma given this word before, the state before, Sn-1. Multiply the three together, do that for every sigma in my set of states, make a choice. It would be easy to choose the last state if I knew the one before. Okay. More generally, if I knew the score of every sequence, S1 through Sn-1, then I could easily choose the last state. But in fact, this decision, as we just showed, would only depend on the second to last state. I wouldn't have to look at the whole sequence. I really just need to know the score of each one for each of the best sequence ending in each possible penultimate state. Okay, so for each state that I could have at n-1, what I need is the score of the best sequence that ends in that Sn-1. I really only have to have number of states values to look at and consider. So the way I like to think about it is that I'm going to do a pre-calculation. Before I get to Sn, I'm going to calculate the score of the best sequence ending in every possible predecessor state. Let's formalize that a little bit more. Assume that for every prefix of the current state, I have a score, which is the best score for the n-1 length prefix ending in call it sigma prime. So if I have this set of pre-calculated scores, then I can say the score at position n of ending in a given state sigma is going to be probability of stop given sigma times probability of the word given sigma times max over whatever the preceding state would have been, the transition from that preceding state to this current state that I'm considering, times the score of that preceding state up to n-1. And now we have a recurrence. I don't actually have to know what the state was at n-1. I just have to know the score of the best way I could have gotten to that state at n-1. OK. So this is just showing it's the same thing to calculate the scores at n-1 given the scores at n-2. The only difference is there's no stop here because I'm not at the end. Same thing to calculate the scores at n-2 given the scores up to n-3.
same recurrence, and it just keeps going all the way back, and it bottoms out at the score at position 1, which is what is, and all I'm asking here is what is the score of the best prefix of states up through word 1? Well, I can calculate that by saying that in order to get to any state sigma, I must have transitioned from start to the state sigma, and then I must have emitted the word W1 from sigma. Simple probabilities. So what happens is I calculate this first. And then I work forward through the sequence. After calculating the vector of scores at 1, I calculate the vector of scores at 2, given these. And I use this recurrence at each step, and then I've done my pre-calculation. And then I'm ready to make decisions. OK, so here is the pre-calculation part of the Viterbi algorithm. This is where you do most of the work. You start off and say, for every state, calculate score 1. Again, it's an emission probability of the first word given that state times a transition from the start state. Then, for every step from 2 up till n-1, I use the same recurrence I had before. There's an emission, there's a transition, and there's a score from the preceding time step. Do this for every time step up to n-1, and then at the end, I do exactly the same thing, only now I have a stop, because I have to take into account that I'm at the end. My claim, which I will loosely prove to you, but hopefully won't put you to sleep with a lengthy discussion, is that if I do all this, and then I say, what is the max over all the states at n of the score of that state? That is equivalent to the score of the best state sequence paired with these words, the maximum joint probability of the states and the words given the parameters. Who already believes me? Who's skeptical? Who's awake? OK, take a deep breath. I'm going to show you a lot of math. So I mostly put this up so you can look it up later, because the slides will be online. Let's not get overwhelmed. My claim was that these two things are equal. OK? My claim was that this is what I wanted. Good, take pictures now. My claim was that this was what I wanted, and this is the calculation that I'm actually doing with these recursive intermediate score quantities. And so I start here with that quantity at the very end. And all I'm doing here is I'm using the recurrence, and I'm repeatedly plugging in the form for the score. So I have an n-1 here, and then I plug in for that in terms of n-2. And then I have this n-2, and I'm going to plug in for that in terms of the score at n-3. And I just keep doing that. And what you start to see is a pattern, that each time I plug in one of these recursive scores, there was an emission, and there was a transition. And then when I get to the bottom, what I've done is I've just rearranged them so that I get a big product over all the time steps. And for each one, there's a transition and there's an emission. And if you remember, that's exactly the form of the HMM. It's just inside this max over the entire sequences, instead of a max over one position, another position, another position, and another position. I've just folded them all together, and now I'm saying let's maximize over the whole sequence. Okay, this is not something that's easily consumed by me talking and you staring at the math. This is better consumed by you going home and looking at this slide again after you've had a couple drinks tonight. I know this is what you're all going to do at 2 a.m. after the banquet. OK, there's a nice way to visualize what's going on in this algorithm. There's actually a couple of them. I'll show a couple. Sometimes we talk about it in terms of this big table. So what I've got are the words across the top. And then these are my states down the side. And what I'm calculating in each cell of this matrix is that score prefix. So this is score of state preposition at position 1. This is gotten by just multiplying two things together, the transition and the emission. And then I calculate this entire column. Each of these cells is calculated by looking at the preceding column and considering each of the states here and what would happen if I transitioned from each of those states to this particular state and the emission, and then choosing a max. And I do that in each cell. Okay, this is actually, if you were implementing the Viterbi algorithm for the first time, this would be a reasonable way to think about it. You've got this data structure, states by words, word positions. Okay, now notice we haven't quite finished. I have not given you the whole algorithm. I've only talked about filling in these numbers. If I asked you for the part of speech sequence, if I was your boss and I asked you for the part of speech tag sequence for this sentence here, and you gave me this table, I would fire you. Right? This is not what I wanted. What I wanted was a sequence of states. So what you have to remember is after you've done all this pre-calculation and you felt very clever because you used a recurrence and all these cool tricks, we don't have the best state sequence until we do one more thing. We have to use the scores to recover the sequence. So remember, I defined score I, sigma, as the score of the best sequence labeling up to position I, word I, ignoring whatever comes later. Okay, so writing that out, it's the max over all prefixes S1 through Si minus 1 of the total probability of S1 through Si, W1 through Wi. With Si equal to sigma. Si is fixed to this value sigma. Okay? Now, if I know what the state that comes after this is, if I know what the state is at Si plus 1, then I can use the scores to choose Si. We're just reasoning in the reverse. So if you keep a back pointer, every time you take one of these maxes in your Viterbi algorithm, if you remember which previous cell in the column that came before led you to this particular value, then you can just follow those back pointers back to the beginning. So here's what it looks like. I know it's a little busy, but what I'm remembering when I get here is that the value from the preceding column that got me here was that one. I keep a back pointer to that particular cell. I can just follow the back pointers back, and I think on the next slide they're colored in, and now I can recover the states. So it's always tempting to imagine that as I'm doing these calculations, I'm choosing states for each of the words left to right, but that's not really how it works. You're really just calculating the scores that you need so that you can then go back and recover the scores from right to left, and recover the states from right to left. Okay, so here's the whole algorithm. Start off by scoring the first column. Multiply the emission times the transition. And then every time I calculate a score from column 2 to n minus 1, I'm also going to keep a back pointer. And you'll notice that the form is very similar. It's just that here I'm storing the argmax, the value over this set that gave me the highest value, in the back pointer. And then I do the same thing in the last column. This time I have to bring in the stop probability. And then after I've done all of that pre-calculation, I do the backtrace. And I can do that by simply recursively following the back pointers. Let the state at I minus 1 be equal to the back pointer from the state at I. OK, so here's another quick example. Time flies like an arrow. This is a classic linguistically ambiguous sentence. It could mean time flies fast in the sort of metaphorical sense, or it could mean that there are these flies. We call them time flies. There's an arrow. They really like it. Which reading you get, actually, if you give me the parts of speech, it disambiguates the meaning of the sentence. You'll notice one of the interesting things, these are actual values that I calculated given probabilities from real data. You'll notice that the word arrow could go with any state. You know why that is? It's not because I observed the word arrow with every part of speech tag. Actually, quite the opposite. I never observed the word arrow in my data. And so I had to smooth the probabilities. And so when I smooth the probabilities, everything goes to non-zero. OK, so what I get when I tag this sequence, I think I get the one where arrow is a noun, yes. Determiner, like is a preposition, yeah. Yeah, and then, so time flies, this is wrong. No, it's a verb, right. So flies is a verb, not a noun. Yeah, so I'm basically saying time is flying, not, there's a third reading, which is I'm giving you a command. I want you to time is the verb. I want you to time the flies like you would time an arrow. I don't know why I want you to do that. OK, so this algorithm, the Viterbi algorithm, is an example of a really powerful idea called dynamic programming. You've likely seen it if you did an undergraduate
in computer science. It's hard to explain exactly what counts as dynamic programming and what doesn't, but the feel is usually very similar. You have some kind of table data structure where you store partial quantities that are reused many times. So every cell in my table gets used for every cell in the next column. So each time that I calculate a quantity, I'm going to reuse it many times. It's going to pay off big time in the next step. There are sort of two properties that you see in these problems. One is that the best solution to a problem relies on having the best solutions to subproblems that look almost the same. They're just a little smaller. And so you work from the smaller problems up to the bigger ones, and you're always kind of doing the same operation each time. The other thing is that these subproblems, they overlap. So every time you compute one of these quantities, you're gonna use it many times. Viterbi is one example. If you've ever calculated the minimum Levenshtein distance between two strings, that's a familiar one people often see, or minimum edit distance between two strings. People often see that in early courses. Dijkstra's shortest path algorithm. Remember that? Anyone? Yep. That's dynamic programming. So there's actually one view of the Viterbi algorithm where you're finding a best path. Think of this as start. Think of this as finish. Each one of these cells, each one of these vertices in the graph corresponds to being in a particular state at a particular time step. Sometimes this is called a lattice or a trellis. And the idea is that you're trying to find the best path from the green one to the red one. And if you do that, you have recovered, if you assign the weights of all the edges correctly and calculate everything correctly, you could use Dijkstra's algorithm to solve the problem that the Viterbi algorithm solves. The difference is that in Viterbi, we're making use of the known substructure of this graph, that each column is fully connected to the next column, but not any of the others. So Viterbi is probably going to be more efficient in general because it's exploiting some knowledge about the structure.
Excuse me?
Yes?
What if score of more states are equal?
If the score of states, you mean if we have ties?
More states have the same score.
Yeah. So if you have ties, when you're choosing your max, usually what we do is we arbitrarily choose or we randomly choose. The algorithm will give you one of the best. If there's a tie, it will give you one of the best sequences. There is a way to generalize the algorithm so that you keep track of all the ties, but it's a little more work.
Would this be where A star would be a good solution, right?
You can use A star to get a faster solution, and it's a nice thing to do when you have a lot of states. Typically, people don't. Typically, they just go, when they have too many states and they don't want to do this exactly, they just kind of go to beam search. But you could use A star. Yeah, there was a really nice paper about 10 years ago showing that A star generalized to this problem and to parsing problems as well. Yep.
Is it the best solution or is it an approximation of the best solution?
No, this is an exact algorithm. Yeah, Viterbi is exact. Best under the model. The model could be wrong, right? So sometimes it's useful to talk about search error versus model error. There will be no search errors when you use the Viterbi algorithm, but there could, of course, be model errors. Okay, so briefly, I want to point to the asymptotics of the Viterbi algorithm. The table, if you think of the data structure we are building when we run the Viterbi algorithm, it's length of the sequence n times the number of states. So it's linear in both the number of states and the number of words in your sequence. That's nice. The runtime is actually a little worse than that because each cell in that table requires size of lambda, number of states, calculations. You have to calculate that max given the previous column. So this is actually quadratic in the number of states. That's why when you run HMM processing with thousands or tens of thousands of states, you typically are going to use an approximation. OK, let this sink in. We are now roughly at the coffee break. Go have some coffee and come back, and we'll do something even more exciting. You can hear me again? It's OK? All right. I think it. Move it up a little bit. So I'm happy to see that you came back. You must want to hear more about HMMs. You must want to learn all kinds of other things you can do with HMMs, so I will deliver that. I didn't promise, but I was able to find the picture. So this is, if you go to Carnegie Mellon and you go to the Gates-Hillman building where I used to work, and you go up to the 8th floor where the machine learning department is, you can find, and on the elevator, you can find this great bag of words. And the funny thing is that the words that are on the floor, they're the stop words. It's very clever. I was not involved in this piece of art. If you go to the building where I work in now at the University of Washington, we have real art. So, OK, quick recap. The Viterbi algorithm, very, very cool algorithm for calculating the most probable sequence of states given a sequence of words under the assumption that your data was generated by an HMM whose parameters you know. You first calculate the first column of scores by multiplying transitions by emissions. We call these score sub 1. And then we calculate for each time step up to n-1, we calculate the scores using this recurrence, where we use the scores from the previous round to calculate the score at the next time step. And we also keep a back pointer so that we can recover the sequence. It's a little bit different in the last column because we also need the stopping probabilities. If we do this, we get a table that looks kind of like this with a lot of little tiny numbers. Notice that the numbers get really small as you move to the right. So there's a trick we usually use. I don't think it's out of fashion. I think we still use it, where we store the logarithms of these values so that anytime we multiply, we actually add the logarithms of the values. And so then we don't have things going off to 0 quite so fast. And if we keep track of back pointers, we can recover the sequence of states, in this case, part of speech tags. So, OK, so what I want to do from here is I want to talk about some other useful inference algorithms that go with HMMs. All of them are, it turns out, relatively easy to implement if you understand dynamic programming. And so what I like about this is that once we understand inference with dynamic programming, there are a lot of other things a lot of other questions we can answer with an HMM without having to do a whole lot more mathematical work. So the good news is that if you followed so far, everything that comes later will build closely on what we've already done. So the next thing we're going to talk about is problem number 2. If I give you a word sequence, I want you to be able to calculate the probability of the word sequence under the HMM. In other words, we're going to use the HMM as if it were a language model that gave us scores of sequences of words. The states are still there, but we're not interested in knowing what the states are, what the most likely states are. They're merely a mechanism for explaining this probability distribution. OK, so why might we be interested in this quantity probability of the words given the parameters? Notice the states don't show up in that expression at all. Again, we might use an HMM as a language model. We might use it to compare 2 or more sequences in any of the applications we talked about before. Later, we're going to be interested in this quantity because when we estimate the parameters of the HMM, we tend to want to choose parameters, gamma and eta, to maximize the probability of the words. Right? If we see words, we want to pick parameters that make the words likely, just like we did for the n-gram model. We can do the same thing with an HMM, even if we've never observed the states. We'll get to that later, hopefully. If you don't have too many questions, we'll get to it. Yes, question.
Even if we've never observed the state, you're still running over, you still know the structure of what you're running over, right? You have to see the derivation of the states for the sequence.
That's right. So there's a wide range of possibilities. Okay, so one possibility, the sort of easiest, is we observe the states at training time. We know what the state is for every word, and we're just doing supervised estimation. The other extreme is that we know nothing. Maybe we know, there's middle ground. Maybe we know how many states there are, or maybe we know a little bit about which words can go with which state, or maybe we know which states can transition to which other state. There's sort of every possibility in between, depending on your setup. But the most extreme is that we don't know anything. We don't even know how many states there are. Typically, the thing we teach is you know the number of states, and that's about it. OK, so let's talk about calculating the probability of the words given the parameters. So as I mentioned before, in order to calculate the total probability of the words, we have to sum up over the state sequences. Remember, this is the quantity inside the sum. This is the quantity that the HMM gives us, the joint probability of a state sequence and a word sequence. If you remember your rules of probability, which maybe were reviewed a couple of days ago, you know that if you want the marginal probability of the words, you have to sum up over the probability of the states. So the idea here is sum up over all possible state sequences the joint probability. Now, if you squint your eyes and you imagine that this weird symbol here is kind of an abstraction, and it could be something else, then you realize there's kind of a similarity. When we did Viterbi, we were looking for the most probable state sequence. We had a max over S. Here we have a sum over S. Here we were solving a combinatorial optimization problem, and we had a polynomial time algorithm. Here we're doing something else. We're calculating a summation. But what we're going to see is that the structure of the calculation is actually really similar. We can exploit the distributive property that we exploited before here as well. And we can build an algorithm that looks very, very similar to Viterbi and gives us what we want for this sum. OK, so here's the basic idea. We want the sum of all the possible label sequences, their probabilities, and that sum breaks down into the sum over scores for different final symbols. Just like in the Viterbi algorithm, where we had a max over that one final symbol, and that was our starting point for developing the recurrence, we can do that here too. So if I write it out, there's a sum over the last symbol, call it sigma, and inside that is a sum over all the sequences from 1 through n minus 1. If we give this intermediate quantity a name, call it f sub n of sigma, f for forward, because what we're deriving is called the forward algorithm, then this is going to start to look a lot like the recurrence we had in Viterbi. So if I plug in the value for this inner sum, I can actually pull out a stopping probability given sigma and an emission given sigma. And then inside that, I have something that has exactly the same structure. This is the sum over the n minus first symbol, call it sigma prime, and then the whole prefix s1 through sn minus 1, the joint probability of that whole thing up through n minus 1, and we'll call that f sub n minus 1 of sigma prime. So I've got this, I've pulled this part out, and then I've got this recurrence where I've got an f, a preceding f. So here's the algorithm. I'm just going to cut to the chase. I start out by calculating f sub 1. This is the prefix probability up through position 1, up through time step 1. And I get it by multiplying together the probability of the word given that state times the probability of the state given the start symbol. This is exactly like what we had before. At each time step from 2 to n minus 1, I'm going to calculate the vector of f values of forward probabilities by multiplying together the emission probability times the sum over the transitions and the prefixes. This is exactly like Viterbi, except here I have a sum instead of a max. And then the final step is exactly the same. The total probability of the sequence I can obtain by summing up over the forward probabilities of all the possible final states at time step n. Everything breaks down exactly the same way. I don't need back pointers because I don't care about recovering states. I'm calculating partial quantities in service of getting a final quantity. The only difference is that instead of a max operation, I'm going to calculate a sum. If you like the graph view of these problems, you can think of this as it's called a path sum problem. I'm calculating the sum of all the scores of all the paths from the green state from the green vertex to the red vertex. Very, very similar. Algebraically, it's almost exactly the same as the Viterbi algorithm. Okay, there's another way to think about it for people who like linear algebra. And the way to think about it, this way to think about it is to say that you're solving a linear system of equations. So I have a free variable for every state and every position in the sequence, size of lambda times n. And I have exactly that number of equations. The equations look like this. They're just the recurrence. So I have a value for f F1 in position for each state, F1 of that state. And then I have, at each position, I have F sub I, which is a function of F sub I minus 1. Or you can say it's an equation that links the values in column I to the values in column I minus 1. And then same thing at the end, only now I have the stop. Okay, the etas and the gammas, you plug them in. Those are your coefficients. And you'll notice that these are linear equations. Each Fi is linear in the Fi minus 1. You could write this out as one big matrix and invert it. And that would give you the solution. It's a big matrix. We don't usually do it this way, but mathematically it's correct. Yes?
I don't really see what the inversion does. Can you explain that?
So the idea is that what I want to do is I want to solve for all the F values. Okay, I've got the gammas and I've got the etas. If I use this, this sort of template, I can write out a set of linear equations. If I then transform that into a matrix form and invert it, again, expensive, not the way we would actually do it in practice, but if I did that, I would recover all the F values.
It's like Ax equals B, and then you have to do X equals
Yep, exactly. Don't do it that way, just think about it that way. So people have seen, who's seen the forward algorithm before? Smaller number of people. Okay, so if you've seen the forward algorithm, maybe you've also seen the backward algorithm. It sounds like a joke. It's not a joke. So the forward algorithm does this pre-computation of partial sums from I equals 1 up to n. Each one involves size of lambda quantities, and each one is a sum over size of lambda combinations. And the asymptotic analysis is the same as Viterbi. The runtime is quadratic in the number of states, linear in the sequence. The space is linear in both. You could, instead of starting at the left and moving right, you could start at the right and move to the left. You'll get the same answer, modulo floating point arithmetic. So the backward algorithm looks very similar. It starts out, we'll call the backward quantities B. You start at position n, and you calculate the backward quantity for each state as the probability of stopping given that state times the emission of word n from that state. And then you work backwards from n minus 1 up to 2. You have a recurrence that looks very similar. Notice each time there's an emission probability given the state you're calculating for. There's a sum over possible states that could come after it, sigma prime. The transition from sigma to sigma prime times the backward quantity in the column to the right, bi plus 1. You work backwards. bi1 has to include the start symbol. And you can calculate the posterior probability of the sequence, w, given the parameters, as summing over the states at b1. You can work left. You can work right. So there are two ways. One way to think about it is that these are two different ways of just rearranging that sum of products of sums of products of sums of products of sums of products of sums of products. And you're just organizing the quantities differently, whether you go left to right or right to left. And they give you different intermediate quantities, both of which have similar interpretations. It's just that one is prefixes and one is suffixes. OK, so here's a pop quiz question. Why did we do left to right for Viterbi? Could we have done it the other way? Could we have given a Viterbi algorithm where we start at the end of the sequence and do a pre-computation backwards, and then have back pointers that are actually forward pointers and trace them back to recover the sequence? Could we have done that, or is that crazy? Who thinks it's crazy?
You mean bidirectional?
No, not bidirectional. Just the opposite of what we did before. The reverse of what we did before. So instead of calculating prefixes, we calculate suffixes. And instead of following back pointers from the end to the beginning, we follow forward pointers from the beginning to the end. Who thinks it's crazy? Can't do it. Who thinks it's reasonable? The reasonables have it. You could do it. I don't know why we teach it the way we do. We could do it the other way. You'd basically take the backward algorithm right here, replace the sums with maxes, and you've got B Viterbi. I don't know what you'd call it. Viterbi backward, reverse Viterbi. Viterbi. Reviterbi. I don't know. Okay. The differences among these 4 algorithms, the one we just sort of invented, Viterbi, forward and backward. There are 2 differences. One's working left to right when it does the precalculation. The other works right to left. One is using maximize and multiply. The other is using add and multiply. Yes?
Are there any NLP problems that tend to work better if you process text back and forward, back and front?
So notice that we changed the processing algorithm, but not the model. So these 2 algorithms would actually give the same answer, given the same model. There are algorithms that are more where the procedure matters more. And in those cases, I think the answer is yes. There are cases where things go better if you work left to right versus right to left, depending on the language. But that's sort of a class of algorithms where the heart of the model is in the procedure. Here, we've tried to separate them. We've tried to say we have the model. It's a choice, right? It's a declarative way of thinking. I actually prefer it when I do research to say, here's my model, and then I'm going to have processing algorithms that are based on the model. But when the 2 are more interconnected, it could very well matter. I feel like I saw a deep learning paper recently where they did some reversal like that, and it made a difference. But I don't remember the details.
Can it be the case that the algorithm is faster if you run it backwards?
I don't think it would be. I think asymptotically it would be exactly the same. It could be just by accident because of the parameters. Could be. Yeah.
I think the deep learning paper was something like machine translation, and they found out that it's easier to translate, to start generating the target sentence from backwards.
Backward to the beginning. Yeah.
Because the recurrent network has to have some state, and it doesn't know at the end. The state is very recent.
Yeah, it's like a stack or something.
Yeah.
Nobody really knows what's going on in there. Okay, so here's another sort of interesting twist. And I think this is relevant to neural nets because neural nets are basically playing with more complicated functions. Here we're using very simple operations, right? But there are other operations that you can use and get different algorithms that look logically they're the same structure, but what they're calculating is something different. So the generalization of this choice along this axis, whether we're maximizing and multiplying or adding and multiplying, maybe other things, is called a semi-ring. So the Viterbi and the forward algorithms are exactly the same calculations, just with a different choice of semi-ring, of two mathematical operators and the set of values over which they compute. So you can say they're the same abstract algorithm, and you've instantiated one of them with one semi-ring, another with another semi-ring. So did anyone take abstract algebra and remember semi-rings? Maybe a few people? Yeah? So this is kind of an interesting connection. So a semi-ring, I'm not going to get into the formal definition. A semi-ring is a set of values and 2 operations on those values that obey certain properties. And if you want to know more, go look it up on in a mathematics encyclopedia. One of them is called a plus, one of them is called a times. The plus is associative and commutative, the times is associative. And the really important thing is that the times operator distributes over the plus. And you have a 0 and a 1, or an additive and a multiplicative identity. So here are the 2 semi-rings in their full form for the forward algorithm, which uses the real semi-ring over non-negative reals. 0 is 0, 1 is 1, plus is plus, times is times. Very convenient names. In the Viterbi semi-ring, again, it's non-negative real. 0 is 0, 1 is 1, plus is max, and times is times. And it has all these properties. Here are some other semi-rings that are interesting. The Boolean semi-ring just has 0 and 1. And the plus and the times become or and and. And this sort of corresponds to a very symbolic logical processing where you're just checking, could the HMM have generated this sequence or not? I don't care what the numbers are. I just want to know if it's possible. You can also use semi-rings to count how many different labelings there are. So if I use integers, if I want to use logarithms, there's a log version of all of this where you're using log probabilities and you introduce a log add operation for the forward algorithm. There are k-best algorithms that find the top k sequences of states. There's a special form. We talked earlier about breaking ties. There's a special form of a semi-ring, I believe, where you can keep track of ties. And then there are other versions that are used in other algorithms like Levenstein and Dijkstra's, where you're, instead of maximizing a probability, you're minimizing a cost. And that's sort of a transformation on the operations. But it's all very, very similar at an abstract level. If you want to read about semi-rings and NLP, there's a classic paper by Joshua Goodman in 1999 called, I believe it's called Semi-Ring Parsing. It's a really beautiful paper. It gives you all kinds of nice connections across different algorithms. Read it after Slav's lecture on Tuesday. OK, so now we can calculate the probability of the word sequence. And the machinery we needed to do it was very similar to finding the most probable state sequence. The next thing we're going to do is calculate the distribution over states for one particular word. So pick a word in the sentence. Say, this is the only word I care about. What is the posterior distribution, given the model, of the states for this word in this setting, given all the words that I observe? OK, so we've been reasoning about the whole sequence, but now we're just going to focus on one word. We're going to do local. We were doing local reasoning before as a step in the larger procedure. But now what we want to do is think about one particular word and what the possible states are for that word. To do this, I'm doing this in part because it's interesting and in part because it lets me introduce a related topic that's quite useful. It's really helpful to think about this problem to use a graphical representation of all the variables that the model is accounting for, all the different words and all the different states. And so to do that, I'm going to draw a graphical model. Have people seen this before, this kind of representation? It's a really elegant way to capture what's going on. Each node is a random variable that takes a value. The ones on the top take values in lambda, the state set. The ones down here take values in sigma. Any random variable's incoming edges tell what other random variables it directly depends on in the generative model. So we call those its parents. A word like word 3 depends directly through the probability tables on its state. The state 3 depends directly through its conditional probability tables on the state that precedes it. It shows you the chain structure. It's sort of an abstract form, and it lets you see how you might generalize HMMs to other kinds of models. So the things that I've circled in purple correspond to the transition probabilities, and the things that I've circled in blue correspond to the emission probabilities, what we've been calling eta. OK, so with this graphical visual language and a little bit more, I'm going to use colors, we can visualize all the problems we've looked at so far. So the first thing we looked at was what is the most probable state sequence. We were trying to maximize over some random variables having fixed the values of others. So what I've done here is I've started using gray to show which things are observed, and I've started using red to show you the things I want to assign values to. So this was the problem Viterbi solved. It said, if I know all the words, I can use dynamic programming to exactly calculate the most probable values for the red things collectively, or find an assignment of all the red variables collectively. Okay, so in probabilistic terms, we often call the things that are gray, the things we've observed, we call them evidence. And then we're doing inference for the most likely values of the things that are red. When we switched to the forward algorithm and asked what is the probability of W, we might use a different color because we didn't care about the states. They were nuisance variables. They were hidden. They're not important on their own. They're only important in their role for explaining the evidence, gray. So what we're asking is to sum over the values of the things that are colored blue. And so the forward algorithm gave us a very efficient dynamic programming solution to finding the probability of the evidence summing over all the other things, all the things that are blue. Viterbi was all red, maximize. Forward algorithm was all blue, sum. Here's where we are now. Lots of colors. I want to know the value of this particular state without worrying about all the others. Just sum those out.
So I'm going to marginalize over all the values of all the prefixes and suffixes and calculate the posterior for this particular state, state 3. Does this make sense? This use of color in graphical models is not standard. You're probably not going to see the red and the blue and the gray used exactly this way in other papers. But I think it's really useful when you want to pair a graphical model showing your assumptions about the data with choices about the inference algorithm you're going to run. Okay, so just as an aside, probabilistic graphical models are an extremely useful way to organize reasoning in all kinds of machine learning problems. HMMs are one kind. The kinds that are usually taught in classes are Bayes nets, Bayesian networks, Markov networks, more abstractly factor graphs. You'll probably see some of these come up again later in the class. So for example, conditional random fields are a variant, can be understood as a variant of Markov networks. HMMs are sort of a special kind because they have this sort of dynamic structure where you don't actually know how big the graphical model is going to be until you observe all the words. But all the mathematics and all the tools we use in general transfer nicely to HMMs and to other models in NLP as well. OK, don't worry about the math. We'll get to that in a second. What we're interested in, again, is finding the probability for each value of this state, the total probability of the words coupled with that state, marginalizing out everything that comes after and everything that comes before. So if I write that out, it's the probability of all the words, W bold, the whole sequence, and state I, given the parameters. I can write that out as a sum over all the prefixes and a sum over all the suffixes. I know this is very small. This is S1 through Si minus 1 and Si plus 1 through Sn, joint probability. This, in turn, breaks in two parts. There's the probability of the first part up through Wi, and then there's the probability of everything that comes after given Si. If you know graphical modeling language, we can say that these two are separated by Si. Everything to the left and everything to the right is conditionally independent given this state. So we can think of it as a factor of just these two quantities, and then we can move this summation inside. Or we can say we're moving this one outside because it doesn't depend on these variables. Now, if you squint your eyes and you remember everything I've shown you so far, which no doubt you do, you'll recognize that this is a forward probability, F, and this is a backward probability, B. We've already done all the work. I don't have to give you another algorithm. You run the forward algorithm. You run the backward algorithm. You look up the two quantities for position I and state I, and you multiply them together. And you've got the posterior, or something proportional to it. You've got the joint probability of the words with this particular state. Okay? There's a way to visualize this where you think of F sub I as doing the work for this part of the graph, and B sub I as doing the work for this part of the graph. Multiplying them together gives you the score of a particular state at this time. Who thinks this is cool? You guys are just saying that. OK, so here, if I want to know the distribution over the states for a particular word, what I do is I run the forward and backward algorithms, each on their own, and get the Fi and the Bi. And actually, you don't have to run the whole forward and backward algorithm. If you know that you only care about position I, you can run forward up to I and stop, and run backward up to I and stop. You don't need the other quantities. You only need to do the pre-calculation up to the point you need it. And then you can say, all right, the joint probability that the state at position I equals sigma and the words were generated by this HMM is the product of F sub I of sigma and B sub I of sigma. If I want to know the posterior, if I want the conditional probability, I have to renormalize this by dividing by the sum over all the states of that same quantity. Then I'll get a well-formed posterior distribution over states, and I can say, how confident is my model about the state at this position, given all the words, for each possible value? This is one of the reasons that people really like generative models, that they can give us posterior distributions over things. They can tell us how strongly they feel about something. Yes?
Why do you need to do that?
Why do you need to do it? Well,
Why do you need to in some particular state?
so sometimes you want to. So one reason is that there's another way to decode. That is an alternative to the Viterbi algorithm, where you look at each word and ask for its posterior, and use that to decode instead of trying to maximize the probability of the whole sequence. Sometimes it works better, sometimes it doesn't. It's called minimum risk. We'll come to it in a few minutes. Another reason is you want to understand where your model's making mistakes. So sometimes your model's wrong, but it's almost right. And so you want to know, you want to say, how confident were you about this decision? Maybe it was actually pretty close. And so it might help you to strategize in figuring out what's really going wrong with your model. Sometimes people evaluate models by looking at their posteriors instead of by looking at their most likely output too. It's not very common anymore. OK, so that was problem 3. So now we know we can use Viterbi to calculate the most probable state sequence. We squint our eyes and change the maxes to sums, and we get the forward algorithm, or the reverse version, the backward algorithm, and we can calculate the probability of the word sequence, summing over all the states. And then we showed that those quantities are very useful as well for looking at a particular word and inspecting what the posterior is for its state, its missing state. So now we're going to use, we keep building on the thing before. We're going to build a little further, and we're going to see an alternative to the Viterbi algorithm for decoding called the minimum risk sequence. And I'll explain why we might want to do this too. So what we were calculating when we had this thing where we took the forward and the backward probabilities and we multiplied them together, let's call those per word posteriors. The total runtime for all of that, if we want to get that for every word, is we run the forward algorithm and we run the backward algorithm. It's going to be n times the square of the number of states, right? Same runtime. Asymptotically, it's still linear in the number of words. Once we have all of those quantities, we can calculate the posteriors for every word's labels, just as we did 2 slides ago. And then one way to go is just choose the most likely word, the most likely state for each of the words, given those posteriors. Okay, so mathematically, given the posterior distribution over S sub I, the state at position I, pick the max, given everything else. And just call that S sub I, S hat sub I. And now you've decoded the sequence. This is called posterior decoding. You're using the posterior. Okay, now here's kind of how I think about this. When we did decoding before, we were asking for the global assignment of all the states that was most probable. But here we're asking each of the words, I want to know what label is most likely, given everything else, but without worrying about the decisions for everything else. Each word gets to decide on its own without worrying about a global assignment that's high quality. Okay, so this is Viterbi. Pick the max sequence overall. This is posterior decoding. Pick the most probable label for each word on its own, conditioned on all the other words. You're not ignoring them, but you're ignoring the decisions about them. Any intuitions, any feelings about which one's better? Sorry? You think Viterbi's better?
I think it's important when you have like a noun group and all words look like nouns, but some of them can be adjectives. And if you already decide this is head of your noun group, all previous should be like adjectives, so you should take this information into account.
Yep, that's a valid argument. Yep.
It really depends on the task you're going to find. Because if you have on sequences, then you'd rather go for Viterbi because posterior decoding may actually give you 0 probability sequences.
That's possible too, although you may not care. Your task may not really care. So here's there is no simple answer to this, right? It's an empirical question, but I want you to understand the insight and the motivation for each choice. This one is going to give you something that is consistent all the way through. The states will all agree with each other. It will be a good It will obey all the assumptions you have about which states pair nicely, all the decisions interact. This one gets to use the whole distribution. It's looking at all the probabilities of all the things and making decision for each state, considering all the possibilities. There's not a simple answer, but there's a way to think about this that's kind of cool. The first thing to notice is that they will not necessarily give the same answer. They will often give different answers. Sometimes one works better, sometimes the other. And you correctly pointed out that if you use posterior decoding, you might get a label sequence where each word is in the posterior getting a good label, but collectively you're getting something that has 0 probability. You've made choices that are not mutually consistent. That could be really bad, or it might not matter. It really depends on how much you trust your model, whether your model is really close to the truth. But there's a way to think about both of these that unifies the ideas, and it actually gives you more insight that's relevant later for learning. So here's the way I want you to think. Imagine that we're going to play a game. We've built our HMM, and now we're going to play a game with our HMM. I know all these algorithms were fun, but this game is even more fun. The HMM is going to get a new sequence of words, W, and you have to use W. You have to label W using the HMM. Okay? And then we're going to take the label sequence, S, and there's going to suddenly revealed to you will be the true label sequence, S star. Okay, so your HMM gets S, it gets W, it gives back S, and you look at S star. And then this is a fun game because you have to pay a fine if you do badly. Okay, so there's money on the table. And depending on how badly you do, you lose money. Okay? And so what your goal is when you're deciding how to use your HMM to make a decision, you want to minimize the total amount that you pay out. Unfortunately, you can never win money. You only lose money in this game. Okay? Or taxes. So your goal is to minimize your cost. You're going to have to pay something, but you want to minimize your expected cost. Okay, so without me telling you what W is, your strategy here might depend on the way that the cost is structured. So thinking about how the cost is going to get charged to you will change the decision I'm going to propose, will change the way you make your decision. Okay, so your strategy has to depend on the cost. So let's talk about a couple of different ways that the cost could work. One way is called all or nothing. If you get the sequence wrong, you give me €1. Wrong at all. You have to get it exactly right. If you get it exactly right, then you don't have to pay me anything. But if you make any mistakes at all, you're going to give me €1. Okay? Who wants to play? What should you do? What should be your strategy? The second most probable.
No,
First, yeah. So the answer is that if you trust your model, you have no choice, really. All I've given you is your HMM. If you trust your model, if you trust your distribution, then you should pick the most probable whole sequence S. That is the one that you believe has the highest probability of being correct, if you trust your distribution. Okay, Viterbi is the answer. Okay. Now, so this is why Viterbi has been motivated in the past. Sometimes it's called Bayes' decision rule. This is why people came up with it. This is why Viterbi invented it. It provably maximizes your expected cost, minimizes your expected costs under these assumptions. If you believe your model and the cost is all or nothing. Here's an alternative. Suppose that instead of paying €1 if you get anything wrong, you pay 10 cents. Is it cents? Cents? Okay. Yeah, 10 cents for every word you get wrong. So you get partial credit. If you get 9 out of 10 words right, you only lose 10 cents. Okay. So this is sort of gentler, right? I'm going to take your money, but I'm not going to take it as fast. This is much more forgiving, and it suggests that you focus your reasoning on each word individually and try and strategize so that you get lots of words right.
Okay, so here you're not going to worry about the coherence of the whole sequence. It doesn't matter. You just want to keep as much money as you can.
How do you know that one word is wrong? It can be that in certain contexts.
You know it because I show you S star after you've made your guess. Okay. You're confusing the evaluation with the deeper philosophical question of what the true parts of speech are, which is a great question. It's just not, yeah. Okay, so what should we do? I've already told you. We should use posterior decoding here. We should say, assuming we trust our distribution, we should look at each word and say, under the distribution, what is most likely to be correct? Not worrying about the other words. And so I should make a decision about each word on its own, given those forward and backward probabilities for that word. Posterior decoding. And you can prove that if this is our cost, if it's a Hamming cost, this will minimize the expected error, the expected amount that you have to pay out. So the general framework that describes both of these is called minimum Bayes risk. The assumption that you have a good estimated distribution will lead naturally to a decoding rule where you pick a state sequence, S hat, to minimize the expected value of the cost, whether the cost is all or nothing, or Hamming, or something else. So you're picking a state sequence that is as inoffensive as possible in expectation. And so I'm not going to go through the derivation. You've already seen enough equations with lots of nested sums and products and things. But it's not too hard to show that if the cost was all or nothing, you'll get Viterbi decoding. If the cost is Hamming, you get posterior decoding. So they're both doing the same thing. They're just making different assumptions about the costs. So interestingly, what's happening when I use Hamming, or really any cost where the cost function looks at local costs and sums them up, I'm exploiting linearity of expectation. The expected value of the cost equals the expected value of a bunch of local costs at position I. You could define a different cost matrix that says some mistakes cost more than others. That's kind of an interesting idea. But linearity of expectation says that when I have an expectation of a sum, I can recalculate it as a sum of expected values. And that's what lets me separate out the decisions about each of the words and minimize this expectation in each position separately. So you can make independent decisions for the Hamming cost once you know the expected local costs. And you get those with forward and backward. So now we've opened up the possibility of yet another thing we can change in our little modeling world, which is when we make predictions, how are we going to get charged for different costs? So let's go back to the problem of named entity recognition, for example. Remember that in named entity recognition, we represent the outputs using B, I, and O tags to show us where the beginnings and insides of different kinds of named entities are, different kinds of named entity mentions are. One of the things that you can do when you solve this kind of problem is you can trade precision for recall. You can say how much more you care about only getting correct named entities at the risk of missing some of them versus trying to get all of the named entities even if we get some false positives, recall. So if we cared about precision, if we only want to get correct named entities and throw away some that we're just not sure about, then we might change the cost function. Right? We might make some errors cost more than others. An error of a false negative is really is worse than an error of a false positive. So one way to look at it is, I know this is a big table. For every possible correct bigram of labels, here is every possible hypothesized bigram of labels. Some of these you can categorize as precision recall. Some of them you can categorize as recall. But notice that I have to look at the pairs. I have to look at where the boundaries are. Getting some boundaries right causes one kind of error. Getting some boundaries right, some boundaries wrong causes another kind. Okay. You don't have to look at this in detail. Just sort of trust me that if you pick a boundary in the wrong place, sometimes it's going to cause you to be too aggressive, and sometimes it's going to cause you to be too timid. Does the intuition make sense? I can change the costs for these different pairings. I can say that some of them cost more, and that might lead to a different decision when I do decoding.
But notice that I have to look at pairs. I can't just look at single decisions, because the B and the I and the O only make sense in the context of what happens nearby. Yes?
The expected value operator could be seen as a regularization operator.
Sorry, the what?
The expected value operator could be seen as a regularization operator.
I don't think you should think of this as regularization, because we're not talking about estimating parameters. We're only talking about prediction and inference. After we've fixed our model, now we're making predictions. So if our cost function was basically a matrix that looked at different bigrams and scored them differently, scored costs for different bigrams differently, then we would actually need a different posterior, a more complex one that looks at pairs. Okay, so what we're interested in is asking about the posterior probability of state I and state I plus 1 taking a particular pair of values given all the words. Interestingly, we can still use the same quantities as before. If I work through the algebra, this is the same kind of structure we had before. There's a left and there's a right. We can factor it into two parts, where we have a sum over the things happening on the left and a sum of things happening over on the right. But there's some stuff happening in the middle. There's a transition between state I and state I plus 1 and an emission of state I plus 1. What it breaks down to is a forward probability, a backward probability, also a transition and an emission. This is a little hard to look at. Let's look at it graphically, and it will make more sense. What I'm interested in is the posterior for this pair, the assignment of these two random variables together. I can calculate it by calculating the forward probability up to this point, the backward probability up to this point, and the stuff that happened in between, the transition and the emission. If I calculate these posteriors for every pair, I could then go, just like in posterior decoding, and make a decision for each pair of words about their states together. And I could do that in such a way as to minimize the expected cost with that pairwise cost for precision or recall. But there's a problem. If I take every adjacent pair of words and label them, there's a possibility that I will label a word one way when it's in one pair and the other way when it's in another pair. I need some, there's a notion of consistency and agreement that's come back, just like we had when we were trying to solve the Viterbi problem. That's annoying, right? We don't want a word to get two labels. We need some kind of consensus among all of these local posterior decisions. So it turns out that there is, I thought I was going to tell you about the solution, or am I just going to leave you sad? That's just cruel. Really? Here's the answer. Here's the solution. Run forward and backward. Score all the possible label pairs at every position with the overlaps. Now use dynamic programming to go back and calculate the sum of these pairwise posteriors that gives you the lowest cost overall. The dynamic programming algorithm that you use will use a min-cost semi-ring, because you're trying to minimize the sum of these expected values of costs. It's going to look a lot like Viterbi. It's going to be a little bit different because the local scoring doesn't involve explicit calls to the emission and transition probabilities. Instead, it looks at these posteriors, which you calculated from forward and backward. So the algorithm will score each pair by the local cost times the posterior probability, or the local risk. You minimize that sum, and now you've got one consistent sequence, and you've minimized the expected value of these pairwise costs. I think this is kind of cool. We've used this in a couple places in our research where it matters a lot whether you care about precision or recall. One case where this happens is when you're doing semi-supervised learning. So suppose that I have some labeled data, but I have a whole lot more unlabeled data. an interesting thing you can do is you can train on your labeled data and then go label your unlabeled data and then try and train on the whole thing. Not a bad idea. It's called self-training. Sometimes it works okay. And sometimes you get better than just using your labeled data. Has anyone seen this before? You use self-training? It's a nice trick. It's very easy to implement. What we found was that if we train the initial model to be more aggressive about recall, in other words, try and find things, even if they're false positives, and then retrain on the labels that it gives you, you actually get better performance than if you just label it naively. Cost functions can matter. That's kind of one of the important insights in discriminative machine learning. Even though we're using generative models here, it turns out that cost can be a useful thing to think about. OK, so here's a pop quiz. Can you think of a cost function such that I would not have a clever solution to this minimum Bayes risk decoding problem? In other words, I want a cost function that does not factor nicely so that I can do forward and backward calculations and get these local posteriors. I need something nasty.
Like if the first and last words differ in one letter.
Something like that might work, right? So say there's a constraint on the first and the last label. They have to be different somehow. That could be possible. Yeah? Anything with cycles. What do you mean by that?
When there are cycles in your graph, like he said, there are constraints between your first and last.
So that's right. So the idea is you want some kinds of dependencies among the labels that aren't just local. But I need it to be a cost. I'm asking for a cost function. So I need you to tell me how, what's an example of a cost function that has this property? Yes, something like that. You have to remember everything you've done so far, and if you ever reuse a label, then you incur a cost. Or you disallow any repetition of labels. Something like that becomes hard. So here's my example. Every word has to get a different label. Or you can use each label at most once. Or you say every label has to be used exactly once. Anything like this, it's kind of a global constraint. If the cost depends on some calculation like that, it won't factor nicely. And dynamic programming won't be your solution. OK, so we've talked a lot about inference, a lot about different ways to decode and use HMMs to reason about the missing information that you assume is there but you don't know. The last thing I want to talk about, because this is a machine learning summer school, is learning. So I think the fact that we've spent most of the time not talking about learning, but talking about the model instead, I think there's an important lesson there, that learning is always relative to your assumptions and the model that you are assuming about the data. With HMMs, you're making a particular set of assumptions that make processing relatively efficient. Not as efficient as if we didn't have hidden states, but there's still kind of a nice point between very, very rich hidden representations and very, very simple models that assume things like bag of words or engrams. They're somewhere in the middle. But learning with HMMs, it's actually relatively easy to extend what we've seen so far and talk about how to do learning. OK, so our typical starting point when we learn HMMs is to say that we have some data and we know how many states the HMM has. There are variants of this where we don't know the number. We don't know how many states there are. I'm just not going to talk about that today. Okay, you can imagine what you might do or look it up in a textbook. We might also have some constraints on the states, like in BIO labeling, you can never have an I follow an O. I always has to come after another I or a B. Otherwise, it's just not a well-formed output. Those kinds of constraints are not hard to encode, but let's not worry about them right now. Let's assume all the states can transition to all the other states. We're going to talk about two variants of the learning problem. In one of them, we have complete data. We have pairs of W, words, and S states. Here, in learning, the states are not actually hidden. They're only hidden at test time. In the second case, the unsupervised case, the more classical case, and the harder one, we have examples of words only. We don't observe the states. They're always hidden, even at training time. Supervised learning is much easier.
The building blocks for HMMs, as we've seen, are these multinomial distributions, what we called gamma, the transition distribution, and what we called eta, the emission distribution. If we make all the assumptions that we make in an HMM, statistics gives us a very clean, closed-form solution for the maximum likelihood estimates. In other words, how do we choose the parameters? We choose the parameters gamma and eta to make the data as likely as possible. It is not a difficult exercise to show that the way to get that this has a closed-form solution, and you get it by counting. It's just like with the Markov model, just like with the Ngram model. Just to give a little bit of theory behind this, it's kind of a nice thing to see because it comes back in more advanced topics. When your data are observed, the transition and the emission distributions can be completely separately estimated from each other and from those for the other states. Each little die can be estimated on its own without worrying about any of the others. And the result is that all you have to do is count things up and normalize them. Okay, this is called separability. And you can actually show it as a property of the graph. I'll do that in a second. Here's the closed form. I'm going to skip how you derive this. You basically write down the log likelihood. You add a Lagrangian multiplier to make sure that your probabilities sum up to 1. You do a little bit of differential calculus, and you end up with counting and normalizing. Count the number of times sigma prime transition to sigma, and divide by the number of times you saw sigma. And what you get is the conditional probability. Very, very simple. Same thing for emissions. Count the number of times you saw state sigma emit word W, divide by the number of times you saw state sigma. Very intuitive. People gravitate towards this notion very, very naturally. I think it's because of what you learned in middle school, when you learned to count the coin flips and things like that. Turns out you can prove it's correct. You can prove it's the maximum likelihood estimate. Here's the graphical models view that lets you see why this is the case. Notice I've colored the words and the states gray because they're all observed. Gray is evidence. Gray is things I see. And I've added nodes for the parameters, the etas and the gammas. These are the probabilities of transitions and emissions. I'm showing them as random variables. It's a little weird, but it's reasonable. They're things we want to know the values for. We want to find the values of these that make the evidence most likely. It's spiritually similar to doing the Viterbi algorithm. Computationally, it's completely different, but it's very simple. The key thing you should notice is that the two red nodes are completely separated from each other by all the gray nodes. That's your visual sort of sign that these two things can be estimated separately. There's a more formal way to talk about separability. If you take an advanced class on graphical models, you'll learn about it. Going one sort of step farther, we've been talking about maximum likelihood estimation, and I warned you for Ngram models that it's very risky to do maximum likelihood estimation. Usually we do something called smoothing. Same thing applies for really any model, including HMMs. Maximum likelihood estimation relies on having a whole lot of data, probably more than we're ever really going to have, particularly if we're relying on supervision and we need someone to annotate the states for us. So there's a good way to inject a little bit of background knowledge and help us avoid overfitting. And one way to do that is called learning with a prior, okay? Or MAP learning, maximum a posteriori learning, meaning that we're trying to find the parameters that maximize the posterior probability or the joint probability of the data, the evidence, and the parameters. People seen this before? Did you see it yesterday? Did Shai talk about priors? Blank stares. No, he didn't. So Shai did his PhD thesis with me, and about half of it involved heavy use of priors, but I think he's moved on. Okay, so this part is new. This is what we're factoring in, this probability of the parameters. Very briefly, because HMMs are built out of these multinomial distributions, dice, the black and the red cubes, there's a very simple kind of prior you can put on these called a Dirichlet distribution. And the simplest version of a Dirichlet is a symmetric and non-sparse Dirichlet distribution. In practice, what you do is you choose these hyperparameters
call them alpha sub t and alpha sub e, and they're values greater than 1. And you add these, you subtract 1 from this value, so you're adding something to each of your counts. Sometimes they're called pseudo counts. It's just like additive smoothing in language models, if you know about smoothing in language models. You just add this extra value to every count before you normalize. And it's a way of biasing your model to be a little bit more smooth. It's a way of avoiding overfitting. In the graphical models view, you can think of it as putting an extra node on which the eta and the gamma are conditioned. Inference is still very, very simple. You're still just counting, adding something, and then renormalizing. Has anyone seen this before? Dirichlet smoothing? Yeah? OK, now let's get to the hard part. Let's talk about unsupervised learning. So going back to when HMMs were invented in the 1960s, the states were really hidden. They were not observed, even during training time. And that's why the models have their name hidden markup models. And this is actually, I believe, the earliest instance of a statistical parameter estimation problem where you say the data are not complete. What I am observing is not the whole story. My generative model claims that some things happened and I can't see them. I only see the evidence at the end. So this seems crazy the first time you hear it. I'm going to give you words and you're going to learn about states. How could this possibly work? Unsupervised learning. It turns out it's really beautiful. We already have all the tools that we need, and we just have to put them together in a slightly different way to get the answer. So what we're going to use, the two things we're going to use are the statistical tool of maximum likelihood estimation, counting things and normalizing the counts to get an estimate of the probabilities, just like we used in the supervised case. And we're going to use this tool from computation, which was the middle part of this lecture, where we talked about inference about the posterior probabilities of things we can't see. And in that case, for HMMs, it's forward and backward algorithms. What we're going to see is that we can put together counting and normalizing and forward and backward to get a really nice way to estimate the parameters even when we don't see the states. And because I gave you a visual notation for this, I can show you in one slide what it's going to look like. There's going to be some blue and some red. Words are evidence. That's all we see. The parameters, just like in the supervised case, that's what we want to pick values for. We want to maximize the probability of the evidence given the parameters. And these guys are now blue. They're not observed, and we don't actually want to find their values. We just want to sum out all the possible values they could take. Every variable is accounted for in one way or another. Either we see it, or we want to estimate its value, or we just don't care. This is a mixed inference problem. It has max and it has sum. It has two things. We want to sum out some random variables while getting values for other random variables. In general, mixed inference problems are very challenging. They're very hard to solve. And they are even, in the general case, they are NP hard to solve. Finding the maximum likelihood estimate with missing data is, in general, an NP hard problem. That is sad. But we don't give up. From an optimization point of view, there's a different way to cast this, where we say that this is a non-convex function. So we don't really have many guarantees for finding the best parameters. But what we can do with a non-convex function is we can find a local optimum. We can start somewhere, and maybe if we know something about the problem, we can start in a reasonable place, and then we can climb up the hill and get to a local optimum. And that's often quite good. That's often good enough. So here's the high-level view. This is called the expectation maximization algorithm. In the particular case of HMMs, it's called Baum-Welch, because those were the guys who invented it. And HMMs were the first model for which we had the EM algorithm. Okay, who's heard of EM? Not electromagnetism. Expectation maximization. The idea with EM is that we had this problem that looked like this, red and blue, terrifying. And now we break it down into two problems, a blue problem and a red problem. On the E step, we solve the blue problem. We infer the posterior distribution over the missing data using the forward and backward algorithms. On the M step, we fix these as if they were evidence using the posteriors that we have over here, and then we solve for the red values using maximum likelihood estimation. The only difference is that now we treat these as soft evidence. Each state is now a distribution over states, given the posterior. And we use the posterior to give us soft counts, soft values for the things that are missing, and say that there are fractional counts. But we can still add them up and normalize them. The M step looks just like supervised learning, except that the counts are somewhat fractional. And the E step looks like the forward-backward algorithm. It is the forward-backward algorithm. Okay, the procedural view is you start off by picking initial parameters for the HMM, the gammas, and the etas. On the E step, you calculate the probability of each possible transition and each possible emission at each position. We already did this when we did the forward and backward algorithm. When we calculated the forward and backward quantities and then used them as posteriors for minimum Bayes risk with posterior decoding and pairwise posterior decoding, we had all this stuff. This just falls out from what we already did. Once we have those, we fix them as fractional counts of all the events in the model, and then the M step re-estimates the parameters given those fractional counts to maximize the likelihood of our pretend complete data. Okay, the E step is hallucinating what might happen at each state. The M step treats it as evidence and re-estimates the parameters. Yes?
But I have to know the number of states.
You have to know the number of states. There are models where you don't, but today you do. One thing you can do, if you don't want to know the number of states, is run it with a bunch of different numbers of states, and then compare them somehow. Maybe see how well they fit the data, and look for a place where it stops increasing to add more states, or it stops increasing by much. More states will always let you fit the data better. So you might have a trade-off. You might say there's a cost to each state or something. Yes?
Do we start with random values for the parameters, or is there any other?
So if you don't really know anything about the problem, I suggest you start 1,000 times with 1,000 random initializations, and then see which one gets you to the best likelihood at the end. You can pop the likelihood out when you run the forward and backward algorithm, right? That's what it gives you, the probability of the sequence. If you do know something about the problem, then you can initialize more cleverly. In NLP, we often find that doing something slightly clever gets you a much better solution when you do unsupervised learning. OK, so just to dig in a little bit more. So what you calculate is for each state, sequence, what you could do, and this would be naive, and you guys all know better because we've been doing dynamic programming, you could calculate for every state sequence the probability of that state sequence given the words, and then count up the number of events that happen in each one and count them according to the proportional to that probability. Right? If this state sequence gets 5% of the probability mass, every event gets a 0.05 count. That's not very efficient because we know there are exponentially many of these state sequences. So instead, for each position, we might calculate the posterior using the forward and backward probabilities, and then count the emission proportional to that posterior probability. Much, much more efficient. We do the same thing for the transitions, only here we have to get pairwise posteriors. Now you know why I taught you about pairwise posteriors. It turns out you need them to calculate the posterior probability of having transitioned from state sigma to state sigma prime at every given point. You need fractional counts everywhere. Okay, so to do this, we can run the forward and backward algorithms to obtain these posteriors. Think of them as soft or fractional counts. And then once we have, these are just the formulas. If you want to go back and look at them later, I'm going to call these soft frequencies and put a hat over them because you're estimating the frequency. You don't actually know how many times each one happened. You're using the posterior probabilities, which can be calculated with forward and backward, just like before, to get the expected frequency of
sigma to sigma prime, or the expected frequency of sigma emitting the word W. And you're going to renormalize these by the total expected frequency of having been in each state. Okay, so now let's look at the M step, where we use those soft counts, those expected frequencies, to re-estimate the parameters to maximize likelihood as if the data were complete. Okay, so this was what we had before. When we had all the data, we counted the number of times we saw a transition or an emission, and we renormalized to get things that sum to 1. Now, it's exactly the same, only there's a hat on the frequency. It's a soft count. It's an expected count. You can still renormalize it. And you could still smooth it if you wanted to smooth, just like we talked about adding pseudo-counts to the frequencies to get maybe a slightly less overfit estimate. That's a good idea here as well. Okay, so EM is, unlike many algorithms in machine learning, it does not give you a whole lot of assurances. All you really know is that every time you do another iteration of EM, the likelihood will not get any worse. Okay, you're hill climbing. You're hopefully getting to a better place. Almost always you are getting to a slightly better place than you were before in terms of likelihood. Eventually, you will converge to a local optimum or maybe a saddle point. And we usually don't worry about the saddle points. Where you end up is going to depend heavily on where you start. So the image that should be emblazoned in your head anytime you think about running the EM algorithm should be Mount Rainier. This is a mountain near Seattle. If you start here, you might end up on this little peak here. If you start here, you might make it up to this one. If you're lucky and you start at a really good place, you might actually get to the top. Where you end up depends on where you start. This is why I suggest, if you don't know anything, to do random initialization. Restart the algorithm many times and take the one that gives you the highest likelihood. There are some tricks for trying to avoid local optima. None of them are provable, but in practice, some of them work better. You can transform the problem a little bit to try and make it smoother. You can start by simplifying it so that there is only one global optimum by solving a different optimization problem and gradually changing it. That's called annealing. There are various techniques, but generally, by and large, they don't give any guarantees, and people usually just use EM. Here is a variant of EM that's sometimes simpler. Instead of getting fractional counts here, you could just use Viterbi and get counts. Get a hard assignment of all the variables and then count it up and normalize. Label the data with your model, re-estimate your model. Label the data with your model, re-estimate your model. This is not going to maximize likelihood, but it's going to maximize something that's sort of related, and sometimes it works well. Sometimes it's called Viterbi EM or hard EM. If you don't want to implement forward and backward algorithms, then this is a way to go. I don't know why that would be. Some people prefer it. I'm not going to say too much more. It often converges faster, actually, but it's a different solution. OK, so just to sort of you have a few minutes. I don't know how many questions we'll have. So the EM algorithm is a very general technique. I've taught it to you for HMMs, and we dug in really deep to the semantics of the different variables in the context of some NLP tasks. But if you have a generative model and you have incomplete data, EM is available to you as a general technique. You have to do a little bit more work to understand how to derive the E step and the M step, but it's a very general tool. When it's taught in machine learning classes, it's usually taught for an algorithm called mixtures of Gaussians. Have people seen that? A couple heads nodding. If you learned k-means clustering, you can view k-means clustering as a special kind of hard EM, the Viterbi EM. You assign every point to its cluster, you re-estimate the clusters. You assign every point to its cluster, you re-estimate the clusters. You can write that as a generative model, and you can derive the k-means algorithm as essentially hard EM for that model. And again, the terminology, the HMM variant of this is sometimes called Baum-Welch or just forward-backward training. Not to be confused with the forward-backward algorithm, but it's called that because it uses the forward-backward algorithm. Questions? Now's a good time for lots of questions. Or I can go on to a slightly related topic. a variant of EM. But the idea is that you sort of bias your model not to make too many commitments early, and then you gradually encourage your model to settle into a solution. There's a randomized variant called simulated annealing that you often learn about in search algorithms, and then there's a more probabilistic variant called deterministic annealing, confusingly. When I was a grad student, I wrote a couple of papers about using annealing to solve these problems and found that it could be quite beneficial. But I think every time, when we got really good results with it, we had to use some really problem-specific knowledge. So I don't know whether that's a weakness or not, but I don't know. I mean, I think there's still more to be done. I think probably it would be worth exploring again. I think one of the reasons people lost interest in variations of the EM algorithm was that around that same time, so we're talking 10 years ago, there was suddenly a rush to a very faddish new idea that became extremely popular very fast. Does anyone want to guess what it was? It was not deep learning. It was Bayesian modeling. Okay, so deep learning is the latest instantiation of the machine learning community all running to one interesting idea. The last time it was Bayesian modeling. It happens every 5 or 10 years. Bayesian models are very similar to what we see. The difference is that everything gets colored blue. That's Bayesian in a nutshell. Okay? Everything is blue, nothing is red. And so what that leads to for parameter estimation is a very different set of techniques, either based on sampling or based on variational approximations. It's all very cool. I got very excited by it. People in my lab still use a lot of Bayesian modeling. Sometimes it really makes sense. It's also popular in some branches of the social sciences. So if you're doing interdisciplinary work, it can be a nice platform. But I think because people got so into those algorithms and figuring that out, they kind of moved away from EM. EM kind of got old. But I still think there's more to be done. And I actually think annealing is relevant to the Bayesian models as well. So if you look at the way people run MCMC inference in Bayesian models, for people who have no idea what I'm talking about, it's OK. You don't need to know this right now. They often anneal or temper, right? They start off by making the distribution artificially higher in its entropy so that they'll kind of get to a random point faster, and then they gradually cool so that you get to the distribution you care about. It's the same basic idea. It didn't really completely go away. Here, yeah. You and then you.
Is it rational to estimate the number of parameters that we should initialize in EM and hard EM, and pick the one that has less parameter for initializing in the hope of converging faster?
OK, so I'm going to answer a slightly different question. So I don't know what's rational, but I will say that people have had great success with starting with a simpler model that makes stronger independence assumptions and initializing that either with a closed form or with EM, and then using that as a starting point for a more complex model. So the classic models, the classic probabilistic models used for machine translation back in the early 90s, they started off with a very simple model that was actually a weird case where EM is convex. And they solved that problem, and then they used the posteriors to initialize the next model, which is slightly more complex. So they move gradually in learning from simpler to more complex models. That is, it has worked well empirically. Whether it is rational, I don't know. I think this idea of sort of staging your models and moving from simpler ones to more complex ones, it's gotten traction in a few places. I think the deep learning people were doing that at some point too, right? Start with a small number of deep layers and then move hidden layers and move deeper. I don't know if that's still popular, but I think it's sensible. Whether it's rational, I'm not sure. Is that close to an answer? Okay.
I think you kind of answered my question.
Okay.
If you don't have any domain knowledge, is there any clever use you can use?
If you have no knowledge, I don't know how to be clever.
Domain-specific knowledge.
Yeah, I don't have. I mean, general advice for EM: if you really aren't sure, be random, and do it many times. You will find very depressing things. So in my thesis, I have a couple of plots of what happens if you randomly start EM from different places, and you get a lot of local optima that have very similar likelihoods and very different error scores. It's really terrifying. For some models, these things are very, very unstable. But if you have a clever initializer, you can often do reasonably well. Yes.
I have a question about these priors which we used. Because even
Yeah.
from data
Yeah.
just from a floor. So how do you
So
does it work? And
it's very unsatisfying, right? So the way the Dirichlet prior is really annoying because all it says is that I kind of expect things to be smooth, or I kind of expect things to be sparse in another version I didn't teach. That's not really a lot of prior knowledge. So one line of research that my group and others have looked at is, can you use the prior as a vehicle for linguistic knowledge? So for example, we built a language model where the prior over words is built out of a morphology system that says some pieces go together in certain ways and others are less likely to do that. And so people have had a lot of success doing that, where you use some rules or some knowledge encoded in some way. We were using finite state machines. There are lots of choices to encode something that starts you off, and that's your prior, and that influences your learning. So I think there's still a lot more to be done, where the prior actually encodes knowledge. It's not just sort of a mathematically simple thing like the Dirichlet. Another form is you believe that certain things are going to correlate. And based on assumptions of correlation or covariance, you may be able to come up with a different form that lets you share more statistical strength and do a better job. But to do that requires sort of both understanding the linguistics and being pretty comfortable with the approximate inference algorithms that pop out when you start getting Bayesian. And that's a small crowd, unfortunately. Is there a lecture later this week on Bayesian methods? They used to do it at the summer school. Is that still? We replaced it with neural nets, didn't we? It's good to know everything. Yes?
The EM training model, training algorithms, is it applicable to only linear HMMs, or is any architecture?
It's applicable to any generative probabilistic model. So I think what you're asking is, what if the parametric form of my model involved some nonlinearities? I think the answer would be, yeah, you could do it. As long as you can calculate the posteriors and re-estimate given fractional counts, I think you should be able to do it. Whether it will work, I don't know, but in principle, it sounds OK to me. Some of the things that they do to train usually the neural folks don't explicitly represent the hidden states as hidden. They have the hidden units, right? So Jeff Hinton actually told me that the reason he named them hidden units was that he learned about HMMs. So these things are deeply connected if you go back far enough in history. But there's something fundamentally different, because there's not sort of an assumption that each word came from some hidden state and we don't know. It's really just, we have this function, let's minimize it. So I'm not sure. But I think if you took an HMM and you changed the parametric form, everything would go through. It's just about 12:30. I won't keep you into the lunch period, but I will. We have time for one or two more. Now the peer pressure is on. Everybody wants to go eat. OK, let's stop there. Thank you.